So, good morning, everyone. Welcome back to the third and the final day of the International Conference on Women in Quantum Science and Technologies. So, we will begin the morning session. In this session, we have 3 talks, and I would like to request our Dean Admin, Professor Rajiv Mitra, to come and chair this session. Professor Rajiv Mitra.
Good morning. So in this session, we have 3 talks, one role model talk and 2 invited talk. So we are extremely privileged to have our very own role model like Professor Indrani Bose. She is very well known to the community of physicists for several reasons. Just to read out a few things that she actually is a recipient of the Fellow of the Indian Academy of Science, Bangalore and National Academy of Sciences, Allahabad. And she was the first recipient of the Sri Shakti Science Samman Award in 2000. Her research expertise encompasses theoretical condensed matter, quantum information theory, statistical physics, biological physics, etc. So I request Professor Bose to kindly give this lecture.
So, let me first thank the organizers for giving me the opportunity to give a talk here. So, the organizers told me that during the first half of the talk, I have to describe my personal journey in science, my personal science journey. So, that will also be a history of an era when we did not have internet, we did not have personal computers, we did not have mobiles. So that I tell you very interesting features of that time. And so I start with remembrance of things past. My graduate studies were in Presidency College, Kolkata. Postgraduate studies in Physics Department, Calcutta University. PhD studies, Physics Department, Calcutta University. And my PhD supervisor was Professor Dr. Kumar Majumdar. Here is his photo. And he was an outstanding physicist, a legendary scholar, a man with rock-like integrity, and the epitome of simple living and high thinking. And he was also the founder director of this institute, S.N. Center. To join the Physics Department of Bose Institute, the founder was Acharya Jagadish Chandra Bose, a famous physicist and a plant physiologist. So I joined as a lecturer in 1987. Highlights of doing science in pre-internet days. Lack of infrastructural support, at least in our institute. In most of the institutes in Calcutta, there was a lack of infrastructural support. The paucity of funds, limited amount of library grants for purchase of books, subscription to journals, limited computational facilities. What was not lacking? Enthusiasm about science in general, and the spirit of sharing. We learned through discussions, listening to lectures, attending conferences, participating in summer, winter schools. Such schools were rare in those days. Organizing informal group discussions. In Kolkata itself, we had a robust network of students and faculty from colleges, universities, and research institutes. We knew each other and had the enjoyable experience of collective learning and sharing of scientific ideas. This was a different time. Now I find that people have become more self-centered. The sharing of ideas, the sharing of resources is rare these days. So across the country, a similar spirit of collaborative learning and research was developing. Some pictures of schools, conferences, visits, which helped enormously in my growth as a scientist. So this is the first meeting I attended as a pre-doctoral student. Meeting on current trends in magnetism at IIT Delhi 1980. Here I am. And at that time, magnetism had become very important. Spin gas was discovered, lots of interesting physics. And there I met many scientists for the first time, some of whom became lifelong friends. And this is another school on exactly some modules in condensed matter and field theory, organized by TRFI at Panchgani in 1985. So lectures given by pioneering mathematical physicists like Sutherland, Newar, Faddeev, Podiatlin, Taktadan, C.K. Mujumdar. The rest of us were participants. I am standing here, Nilima Gupta is standing on this side, and if you focus a little, focus your attention a little, you can recognize many of the scientists who you know. Mustan Singh Verma, D.C. Ramsasti, Ramkrishna Ramaswamy, all of them are here. Ramadas from PI5, Sunil Mukhi, Nippon Ghosh. And so we continue to educate ourselves on these techniques of examples of modules like Bethian's quantum investigating in small groups after returns to Kolkata. Remember, there was no internet from where we could pick up lecture notes. The only way of learning was through discussions. And many years later, all this learning did not go in vain. Many years later, we have 6 lectures on exactly such models at the HCHC School of Statistics and Physics, organized by TF and Mumbai. This is my first lecture on the IG model. I started with the IG model. And there used to be this annual Department of Atomic Energy Theory Symposium, which all of us used to attend, because there were very few conferences at that time. And here we got the opportunity, and this was the reading symposium. They offered further grants for picking up new knowledge and having fruitful discussions. So this is the Panchgani Annual Reading Symposium, 1985. Here I am sitting by the Gulf of Trieste at International Center of Theoretical Physics, Italy, and visits to ICPP benefited me enormously. We could meet many brilliant scientists, listen to their lectures, interact with them, and so on. Advent of internet, easy access to new knowledge and up-to-date information, but the fun of collective and collaborative learning was missing. Advantage is enormous. I could start working in totally new areas because of the internet. Because I taught myself by visiting the internet at the number of times. The last 25 years of the 20th century are magical era with successive discoveries of a host of novel condensed matter physics phenomena. We witnessed all the discoveries one by one: spin glasses, Anderson localization, integers and fractional quantum Hall effect, quasi-crystals, high temperature superconductivity. And there was the emergence of many subfields of research: strongly correlated systems, quantum magnetism in a rejuvenated form, quantum phase transitions, fractional statistics. 21st century procession of magical discoveries in quantum science and condensed matter physics continues. Graphene, topological insulators and materials, electronics, twistonics, and Shantika probably is giving a talk on orbitronics. So that is another addition. And dominant, what was the dominant feature of the newly emerging areas of quantum science? A rich interplay between theory and experiments. When we were students, there was a sort of boundary between theorists and experimentalists. They rarely interacted with each other. So now, after the discovery of, after these wonderful discoveries, analyzing and interpreting a plethora of experimental results became as challenging as developing rigorous theories. Experiments motivated new theories, then predictions of toy models confirmed in experiments. 1990s, tremendous research activity in the newly emerging areas of quantum computation and information. So you know all this, but for the sake of completeness, I'll just go through the slides. Fundamental unit of classical information is bit has two positive values, 0 and 1. Fundamental unit of quantum information qubit with two distinct quantum states, represented as 0 and 1. A spin up particle with two quantum states, spin up and spin down, an ideal candidate to serve as qubit. So quantum principal qubit can also be the linear superposition of states 0 and 1. The ground state of two antiferromagnetically interacting spins is a singlet. total speed is equal to 0. And here is a picture, spin configuration of the singlet. Other names for the singlet, spin timer, valence bond, etc. A spin singlet is a perfect example of an entangled state. You must have heard of entanglement several times during the course of this school. And entanglement is a characteristic feature of quantum mechanical systems has no classical analog. Two entangled particles have joint properties rather than individual identities. And entanglement signifies non-local quantum correlations strictly action at a distance. Normally, I like to explain whatever I said, but because of lack of time, I cannot go into detail, but I hope by this time people have understood what is entanglement and something like that, and other related concepts. So with my background in quantum space systems, started working in the area of quantum information theory. From 2002 onwards, started working on biologically inspired physics problems inspired by the ideas and vision of Acharya Desibu. So I was in an institute, BOSEStat, where most of the faculty were biologists, and I interacted with them and realized that there are many interesting problems to which physicists can contribute. And this is Acharya Desibu, this is what he said. The excessive specialization of modern science has led to the danger of losing sight of the fundamental fact that there can be but one truth, one science, which includes all branches of knowledge. And Schrödinger, he wrote a monograph titled What is Life? The physical aspect of the living cell. So, we were inspired reading this monograph. I just show you a cartoon. The cellular hullabaloo, taken from an article in Nature. The inner life of a cell is noisy. This is the mother cell, and these are the daughter cells. Two genetically identical cells kept in the same environment can behave in dramatically different ways due to noise. What is noise? Many of the processes in the living cell are probabilistic processes, and they give rise to fluctuations in the concentrations of key biomolecules. And these fluctuations I call noise. So, due to noise, one daughter cell might go dormant while the other stays active. So, the major focus of our studies was how living cells derive benefits from noise. Noise need not be a nuisance. Noise is also utilized by the living cell for certain benefits. And there are also intimate links between predictive theories and experiments involving single cell measurements. I also started working in the area of statistical mechanics, population model, pattern formation, vibratory mechanism. In fact, my first lecture in BOSEStat Center was in 1995. There was a conference, Dynamics of Complex Systems. I was invited to give a talk, and I talked on this Turing mechanism. Current research, biologically inspired physics, interdisciplinary physics. Recently, I have published a paper in it's going to be published under a StatMate theory and experiment. This is on the title of the paper is Growth, Poverty Trap, and Escape, based on the famous economic growth model proposed by Solow, Nobel laureate in economics. And now I have started research in a new area, Valuetronics, in collaboration with Professor Achinta Chinmo Bose Institute and the students Chunki Nayak and Shubhadeep Masanta. And we have our first publication is here. And I am grateful to Achinto and his students for introducing me to this exciting area of research. And we are very happy collaborating together and learning about the new developments in the area. And yes, we wrote a review, I wrote a review with Pustansi Barma, bosons in magnetism. This appears in the special issue of Physics News on SN Bose, volume 49, this is the reference, and the review is available in ResearchGate. So whoever is interested, please visit ResearchGate and read this review. So now I'll just 50 minutes, no? 30 minutes. 30 minutes, okay. And so now I'll just briefly describe highlights of some of my research. PhD studies. So this was a paper exact analytic solution of the three-magnum bound state problem in one dimension. 1978. So magnetism we know is a purely quantum phenomenon arises due to the interaction between spins. Quantum magnetism, a core subject of condensed matter physics. Spins interact via the exchange interaction, form of the interaction derived by Heisenberg and Dirac. In fact, if you trace the history of quantum science, derivation of the form of the exchange interaction is one of the terms of the early research in quantum science. A linear ferromagnetic chain of spins. Spin has magnitude half. Spins interact via the Heisenberg exchange interaction Hamiltonian. And the eigenvalue problem is xi equal to E psi. Ground state is the lowest energy state. All spins pointing in the same direction say up. This is the ferromagnetic ground state. You have seen a textbook picture of me. Excited state, how do you get the excitation? The excited state is a spin wave of one magnum state. Reverse a single spin in the ground state. Reverse spin travels around the chain in the form of a spin wave. This is the one magnum state, and magnums are bosons. They are integral spin. Two reverse spins, two free spin waves, or a bound state of two magnums. So what is a bound state? In a bound state, the two reverse spins occupy nearest neighbor sides and travel together. They stay close to each other and travel together. Now, three reverse spins. Possibility of a three magnum bound state. My first interaction with again, Professor Mujumdar, wrote down the following horrendous integral expression on board. And challenge first, solve the integral equation. And he told me, and this, quoting it, the Bengali sentence he said was, Sahidya Halini. And we have to solve the problem. And challenge to solve the integral equation to get exact analytic form of three magnum bound state function. First task, devise a method of solution. No textbook method known. Initial stages was like the game of snakes and ladders. Jubilant climb ups, actually false starts, followed by disappointing climb downs. And then here, intense effort and 700 pages of calculation later, solution finally achieved. Learn the valuable lesson. Persistence pays off. So quantum physics abounds with bound state problems. Simplest example, hydrogen atom, a single electron bound to positively charged neutrinos. A two-body problem is a two-body problem. Schrödinger equation can be solved exactly. Helium atom, a three-body problem, a bound state of two electrons and positively charged neutrinos. No exact analytic solution of Schrödinger equation. Not many exact analytic solutions of three-body problems. The colleagues of Professor Mujumdar found the solution a monumental achievement, but I was very unhappy because to me it was like a mathematical curiosity. The one could not go in different directions starting from there. At that time, the three magnum bound state was not the focus of interest of scientists working in the area of magnetism. But now there is a resurgence of interest in magnum bound states. Three magnum bound states in the quasi-one-dimensional antiferromagnet, which has been experimentally detected. Experimental observation of Bethe strings, Nature 2018, Bethe strings, describe bound states of magnetic excitations. Three magnum bound state, four magnum bound state, multi-magnum bound states. And dispersions of many-body Bethe strings, Nature Physics 2020. Recently, multi-magnum bound states have been proposed as carriers of quantum information in future quantum technologies. Next is to superconductivity, another core subject of condensed matter physics. 1987 landmark year, discovery of high temperature superconductivity in a nuclear system. Superconductivity, one of the most well-studied phenomena in condensed matter physics. 5 Nobel Prizes awarded so far. Phenomenon discovered in 1911 by Canadian Ohms. So, zero electrical resistance in the superconducting state. As you cool a metal below the critical temperature Tc, the electrical resistance becomes zero. So, there is a phase transition at Tc from the normal metallic to the superconducting state, and no electrical power required to maintain an electrical current in the cell circuit because the resistance is zero. The famous Buddy-Cooper-Shepard theory. In the superconducting state, electrons form bound pairs, Cooper pairs. Pairs behave as bosons. No exclusion principle, they form a condensate in the superconducting state. The superconducting state similar to a boson and condensate in which the bosons occupy the same low energy state. But the sad fact was that the highest TC that could be achieved till 1986, 23.2 degrees Kelvin for NV3 GeV. So Matthias, the physicist, he proposed the experimental physicist, he proposed 6 rules for finding new superconductors. High symmetry, high density of electronic states, stay away from oxygen, stay away from magnetism, because magnetism destroys superconductivity, stay away from insulators, stay away from Matthias rules were plugged in the Euclid systems, exhibiting high temperature superconductivity. No one could anticipate that these Euclid systems will become high temperature superconductors. So Li2CuO4, lanthanum copper dioxide pairing compound, antiferromagnet, and peculiar kind of insulator, not a band insulator. It's called a hot insulator, where the insulating property is due to the effect of strong Coulomb correlation. The electrons avoid each other to minimize the Coulomb repulsion energy. And now you can dope the system by replacing some of the lanthanum ions by strontium ions. So X is the doping concentration. So when you dope the system, superconductivity is Fc and Tc conductivity 40 degrees Celsius. Then a series of Euclid systems were discovered, and highest Tc acid so far in Euclid system under pressure.
ইন্টারনেটে আসলে আপনার এখান থেকে একটা কি ইকো হচ্ছে
আচ্ছা।
তো অন্য একটা দিচ্ছে
আচ্ছা। Thank you. So am I looking at someone's about this? Highest, please. Can I use my, don't you read it already? So highest is I think so far is so far in Euclid system is around 550 degrees Celsius. And all these Euclid systems have a common structural ingredient, namely the copper oxide plane. This is the copper oxide plane. So copper ions, shown by solid green circles, they carry spin half. The spin halves, they interact via the antiferromagnetic exchange interaction. And in antiferromagnetic long-range order, nearest neighbor spins are antiparallel. This is what is shown here. So that see, oxygen is there. Matthias will something. And in the undoped state, you should, simple-minded elementary band theory will tell you that you have a half-filled band, so it should be a metal. But in reality, it turns out to be an insulator. And that is what I explained a bit earlier, that due to strong Coulomb correlation, the electrons do not move. They stay localized at their respective sites. So no macroscopic charge transfer is possible. You have an insulating state. This is the Mott insulating state. This is an antiferromagnet, and this is a strongly correlated system. Strong correlation arises from the strong Coulomb repulsion between electrons. So no site can be doubly occupied by electrons. One with spin up, the other with W. Double occupancy is inhibited. And so how does dark transport occur here? As soon as you dope the system, doping means you are removing some of the electrons. And so the empty sites, they behave as positively charged poles. The charge transfer opens to the motion of positively charged holes. And so in the superconducting state, holes form bound pairs. The holes are found in the Cooper pairs. In conventional superconductors, electrons form the Cooper pairs. And one has to find out what is the glue that is keeping the electrons together in the form of a Cooper pair. For conventional superconductivity, we know that the attractive interaction is mediated by electron-phonon interaction. But what is the interaction here? So here is a whole motion that the whole starts moving from here to here, but it leaves behind a string of parallel spin pairs, three parallel spin pairs. Antiferromagnetism demands that to get the lowest energy state, speed should be antiparallel. So as the whole starts moving, it is a costly process in terms of exchange interaction energy. Exchange interaction energy goes up. So the question is, motion of the issue is then how does the whole move? The motion of the whole unfavorable. People used to say that the whole motion is frustrated. And remember, the strong correlation is at work, no side can be occupied by two electrons with opposite speeds. So theoretically, trying to get an understanding of the experimental phenomena became extremely difficult. People came up with approximate theories. They could not make any exact statements. Then what happened was the following, and this is the famous phase diagram of high-precision superconductivity. These are strange insulators, strange metals, strange superconductors. Lots of puzzles remain to be solved, and equivalent of business theory yet to be developed. And discovery of high temperature superconductivity has revolutionized research in condensed matter physics. As Robert Schiffer said, that solid state physics volume 2 has to be written. So many new concepts, so many new techniques. When we studied physics, condensed matter physics, we did not know, we were not familiar with these concepts or techniques. Then people propose spin ladders, which are toy modules of strongly correlated systems. If you cannot solve a difficult problem, try to construct a toy module which can be solved in a diagonal problem can be solved in a rigorous manner, and try to address issues, unresolved issues of strong correlation. So simpler than the copper oxide plate, unresolved issues of strong correlation can be addressed more easily. So here is a spin ladder, two chains coupled by rungs. And at each side the spin is sticking and the spins are interacting via the electromagnetic exchange interaction. J parallel for interaction within the chain, J perpendicular for interaction along the rungs. Okay, the hydrogen exchange interaction is this one. So what is the ground state of the spin ladder? It's a pedagogy problem. What is the lowest energy state? It turns out that this is a difficult pedagogy problem. We can solve the two spin problem easily. That the two antiferromagnetically interacting spins, you know, the ground state is a singlet, then can be state. So we introduced a ladder module with diagonal exchange interactions, diagonal. That not only you have intra-chain and ground exchange interaction, but also diagonal exchange interaction. And we could find out the exact many ground state. In the exact many ground state, you have singlets along the rungs. Singlets. This may conflict along the rungs. So remove a single spin, a positively charged hole created in the toy module. Hole can hop to the external sides, also hop along a diagonal. Ideally, problem H I equal to V I can be solved exactly. So motion of single hole in the background of singlets unfrustrated. It can readily move along the ladder. Exchange interaction energy is not raised. What happens in the case of two holes? And see that this is not a one body problem because I'm saying single hole. It is a single hole plus n minus 1 antiferromagnetically interacting spins. So it is truly an n body problem. So what happens in the case of two holes? Because remember, in the ITC superconductors, two holes, they form the Cooper pairs. So can we solve the eigenvalue problem in this case? Again, eigenvalue problem can be solved exactly. And here is a picture. This is the two-hole bound state. And these thin lines, they form the lower and upper boundaries of a continuum of scattering states. The holes can scatter against each other. But here is a bound state solution and there is also an anti-bound state solution. The two-hole bound state has D-band-like symmetry as in the case of cuprate superconductors. So magnetic, how much can Any, and two, so that, so we could prove many of the things exactly in this toy model, which are characteristic features of the actual ITC equipment systems. And here we could show that magnetic action interaction provides the glue for the binding of two holes. Why? If the holes are located on separate rungs, the action interaction energy with two rungs is lost. But if they are on the same rung, the loss is less. So the two holes like to form a bound state and move together. And the interesting thing is that these are all theoretical models, but then a group ladder model was discovered, ladder compound, and this exhibits superconductivity under pressure. So here is an example where theoretical predictions are confirmed in actual experiments. And TC was around 12, well, it is Kelvin at a pressure of 3 degrees. Speed ladders, examples of real materials, by now many exhibit a host of novel phenomena. So we know that this realization of BOSEStat condensate in an ultra-cold dilute gas of alkali atoms in 1995. This was a landmark achievement, discovery awarded Nobel Prize. So as a subfield of research, an emerging subfield of research involves ultra-cold molecules in an optical lattice. So beams of interfering laser light generate a periodic potential in which atoms are trapped. Periodic potential mimics the periodic potential experienced by an electron in a solid. And so this system can mimic condensed matter systems. That it can clarify several issues connected with actual condensed matter systems. So recently I found a paper has come out, magnetically mediated hole pairing in periodic ladders of ultra-cooled atoms. So what our toy model predicted and all other theoretical models of the speed ladder predicted, they were confirmed in this experiment. So now I don't have much time. I would have loved to explain whatever we have done in this area of electronics, because this is a very exciting area to work in right now. But originally I planned to give a full talk on electronics, but I was told that one has to speak about one's personal and I wish I was not selected as a role model speaker, but as one of the speakers. Right. And so electronics, emergence of a new area of research with possibilities for both exploration of fundamental quantum physics and novel applications in quantum technologies. So values is defined by the maximum and minimum in electronic band structure. Simply transition metal disulfide semiconductors with the chemical formula NH2. A is molybdenum or W. W is your tungsten. And X is SCRT. What are the material properties? The most important property is lack of inversion symmetry in the system. Here is the side view of the crystal structure, and this is the top view. Structure not the same under inversion operation. You can easily check from this diagram. So there is no inversion symmetry. That is the crucial feature. And there are two prominent valley structures with energy degeneracy at two inequivalent points, K plus and K minus at the corners of the Renoir zone. This is nothing but the mid-cell momentum space. And the valleys related to each other via time reversal symmetry. And remember the time reversal operation flips both linear and angular momenta. So this is the energy degeneracy that K is replaced by minus K and spin up by spin down. So here is the valley structure at K plus value and K minus value. Prominent contributions to band states from d orbitals of transition metal ions. Spin degeneracy of valence band states removed due to broken inversion symmetry plus strong spin-orbital coupling of d electrons. These are the valence bands, these are the conduction bands. And there is considerable splitting due to spin-orbit interaction combined with inversion symmetry bending. So bending of inversion symmetry gives rise to very specific physical properties. This is important. So the physical quantities, I don't have the time to explain all these concepts. Very temperature, very magnetic moment. Just remember, very temperature is a geometrical quantity associated with the electronic bands. And the electrical, magnetic, and optical phenomena, for example, very specific optical selection rules. This is what I have shown here. Use circularly polarized light for photo excitation of electrons from valence band to conductor band. So this is circularly polarized light, right-handed circularly polarized light, sigma plus, left-handed circularly polarized light, and right circularly polarized light excites electrons only in the plus K value. And circularly polarized light excites electrons only in the K minus value. So you have a valley polarization. You can distinguish between the valleys by using circularly polarized light. Both valleys are not occupied. Depending on the helicity of the light, one of the valleys will be occupied. So valley polarization, preferential occupation of a valley by electrons. Ideally, valley polarization should be 100%. So deviation of ideal value due to intervalley scattering from K minus to K plus and so on. And so the interesting thing is that electron has now both speeds, spin up and down, and vary degrees of freedom. So what is a vary degree of freedom? But if you can define a vary Schrödinger spin, like the quantum spin half, you can say that there are two distinct states, plus up and minus up. So vary Schrödinger spin also has two components. If it is up, then you say that plus K value is occupied by an electron. If it is down, you say the minus K value is occupied by an electron. So immediately it tells you that this value degree of freedom allows for binary information storage and processing. The value terms in quantum computing assign the value index tau to K plus tau is equal to 1 and K minus tau equal to minus 1 values. And value index is quite robust against intervally scattering can be used to define a field gauge. So one electron is excited from valence band to conduction band, leaving behind the positively charged hole. Due to Coulomb attraction, they form a bound state called excited is a boson. And then, so let's say this is the zero state of the qubit. And similarly, this is the one state of the qubit. If it is plus K value, 0, and if it is minus K value, it is 1. Maybe 10 minutes, no? Maybe 2 minutes, 5 minutes. Electron and positively can go from the excited boson. So you can also create linear superposition of the qubit states by shining light with linear polarization. Linear polarization is an equal mixture of both RCP and LCP components. And excited has finite lifetime. Then the excited can recombine. The electron and hole they come together and emit light. And you can detect the light in photoluminescence experiment. You can detect the polarization. So degree of valley polarization measured from photoluminescence measurements. This experimental curve is from Achito and his students' experiment that sigma plus light used to excite the exciter and the photoluminescence emission intensity is given by this, and there is a lesser intensity because some electrons have gone to K minus value, so there will be some contribution in photoluminescence experiment from sigma minus. I think I just take this opportunity that Ochito, Chumki, and Chumari, they're carrying out fantastic experiments. We have very poor infrastructural facilities in Post Institute, but I really, this is the paper. I've Chumki presented this paper in yesterday's poster session. So they constructed a device, actual device, nano device, a nano-sized photonic device, generation of a photonic through optical excitation by circularly polarized light. So electrical control of magnitude of photonic by an external gate voltage. A possible application detection of polarized light scattered from photosynthetic microbes is circularly polarized. I just came across this information somewhere. Immense opportunities for developing quantum technologies. Okay, TNPC binary error work in progress. I don't have the time to tell you about the exciting developments in this area. Research quantum physics, counterintuitive experimental results, but I will not have the time to go to this. I'll just keep all this. In this case, you don't have valley polarization because this binary is imperfect symmetry. So valley polarization is not possible, but you have layered spin polarization. Individual spin layers, you can show that they are polarized. And DFT calculation, first principles DFT calculations are coming in very useful to show this. And actual photo emission experiments, photo emission spectroscopy experiments. This is the experiment that different layers using differently circularly polarized light, you can come up with spin polarization. So polarization leading to measurements which are not sufficiently localized. Okay, I'll just end. Then last week's nature activities article, tunable superconductivity in electron and holdover kernel bilayer graphene and observation of superconductivity, BPG combined with a PNBC monolayer. Fantastic experiments and possibilities of new development of new quantum technologies. My research journey became the happiest pursuit in life because of the support of numerous friends, colleagues, and students spread all over India. I wish I could mention some of their names, but I'm not doing that. I remember with nostalgia the exciting time spent with my PhD and project students in the exploration of new physical phenomena. I end by quoting Professor Kantan Kumar Majumdar. It is a journey along the road to infinity that matters, and that journey has to be performed with dedication and scrupulous honesty. And I just make fun of it, but I just go for 2 minutes. I'll just take another 2 minutes. Then this is a workshop, quantum science and quantum technologies. So I create a comment by Novoselov. You know that the one that material of 21st century is graphene, discovery of graphene. And Novoselov comments the physics part is easy. But what is difficult is implementation in the form of a quantum technology. So you have to have you have to imagine a product, you have to have some product in mind. What are you going to do with this physics? Some idea. And then you have to get in touch with industry. This is not the job of academic physics departments to sort of implement these ideas in form of quantum technology. So I am really excited that so many scientists, I don't like to say women men scientists, but since the title says women in science and quantum technologies, it's a revelation to me that so many talented women scientists are working around the country doing fantastic state-of-the-art experiments. So my suggestion is that please form networks amongst yourselves. Don't depend on elders. I mean, the real people you get together and start discussing things and get in touch with industry. I have from personal knowledge, I will not, I will reveal the detail, but I know nursing to grow, got in touch with some physicists working on quantum computation to submit a project in this quantum matter initiated by Government of India. So you have to seek out industry and the appropriate people and I think the future is bright. Thank you.
Thank you for taking up and combining your past with future. And we can take some questions.
This is a question about your work on this ladder. And so you had to add a diagonal interaction to make it exactly solvable. So we know there is an odd even effect of this ladder physics.
Right.
So can you extend your spin to 3-leg and really show that the spin gap vanishes?
Very good comment. Actually, I did not have the chance to tell you that several materials have been discovered after the theoretical models came up. several modules with ladder-based structure were discovered. Single chain, two chain ladder, three chain ladder, four chain ladders. As she said, there is an odd even effect. Odd number of chains, spectrum is that list. Even number of chains, there is a gap. Very good point. In fact, I described this work in this. I mean, there was an international conference on quantum magnetism in IC Bangalore, and they explained this work, and people were saying, can you extend to 3 holes, 4 holes, or as you said, that can be extended to more number of chains. At that time, I could not do it, but this mimicking of conditional systems, actual experiments can be carried out. There is in some article there is the opening sentences evaluate or simulate. One thing is that you carry out some approximate theory, but if you do simulation via these ultra-cold molecules, maybe more insight will be obtained. And so that was a very good point, and no, we have not been able to do that. That is
My question is about you are discussing regarding very study. So 0 state and 1 state. So maybe the concept here. My question is it possible experimentally get also the superposition that get 0 and get 1, that superposition, and also is it possible to perform different basic measure,
different.
basic measure. Like in spin system, we can Pauli signature basis measurement or Pauli signature basis measurement. It can be performed whether in this kind of system it is experimentally doable.
Like I told him that if you do linearly polarized light, you get a coordinate superposition of the 0 and 1 qubit states. So this idea is still developing, and I do not have adequate knowledge. But I am also a new entrant in this area. So new protocols is being developed. But I just mentioned one thing to you that these are monolayers or bilayers. But recently, in 2000, this year, a paper came out in Nature that you can show value polarization in bulk BNBC materials also. Not one monolayer or 2 layers, but they use a quantum optics method which I have not been able to understand. This paper structure, TRDFOIL, so they have developed laser pulse beams which have this kind of symmetry. They are engineering the laser beam pulses to sort of, give rise to manipulation. And they are more robust, it is a universal root. But I have yet to understand that paper, I do not know well. And that is the talent. That given the basic facts can be come up with actual applications that is more difficult than just doing the theory. Theory, but I don't think it is that difficult. And but these electronic factor calculations, native test, they are very important to get some clarity about what is going on.
I have follow-up question like these valley polarization states, they are long-lived compared to the other states.
Very good point. At least I could cover in my talk for quantum technology-based applications. These excitons and the qubit states should be long-lived. So here, I think people are trying to extend the lifetime in bilayer, not 2 layers. So there is now a possibility, inter-layer exciton. Electron sitting in one layer and one sitting in another layer. Since these are spatially separated, the lifetime is longer. And people are developing protocols based on bilayers and so it's a very exciting area. This much I should also this kind of topic.
And also the paper
Like room temperature.
very good.
So possibly it is limits. Please, see if possible, both of you are, so to say, leadership positions. I mean, come up with ideas where young scientists can sort of actual planners, even the industry people also.
Thank you. I think we are.
Sorry for taking
I-
time.
So we are exactly. I have the pleasure to hand you over the memento. Okay, so we now have two bright physicists to deliver their invited talks. So first I invite Dr. Kosturi Shah, who is an assistant professor at the electronic engineering department at the IIT Bombay, and she is working on nanophotonics, quantum optics, magnetometry, and color centers in diamond. I think her talk is on the quantum imaging with this diamond. So Kosturi.
Yes. Okay, good morning, everyone, and thank you, Roshni, for this fantastic opportunity. I am so unfortunate that I could only come for one day. However, I'll just try to give you an overview of the kind of things we are doing, and thank you, Professor Bose, for this fantastic introductory talk. So, since you mentioned applications, and it really segues into my talk, which is really about applications of quantum technologies, and we are indeed working with industry to really, get quantum technologies to the market, and hopefully soon. So today I'll be talking to you about the quantum imaging with NG centers in Diamond, and these are, as you know, that Diamond is a very key word here. So this is the platform that we use. So I'm an associate professor in IIT Bombay, Department of Electrical Engineering. And today I'll be talking to you about magnetic field sensing. So as you know, that magnetic field really ranges in nature from very high values, like Tesla levels typically used in MRI machines. You would have heard that these are very high, Tesla machines, or even in, if you want to use in applications, for instance, in outer space, the magnetic field is quite high in value, in absolute magnetic field value. Whereas in nature, in our human body, or even things around us, the field values are much lower. So Earth's magnetic field, as you know, is about 50 microtesla, or zero 0.5 Gauss. And in the human brain, the typical signals are of the order of picotesla. So it's really a wide range of magnetic field that we are talking about. Hence, one sensor, of course, does not fit all this range. And so, as you see here in this plot, there's a whole zoo of sensors that can sense magnetic field, which have a diverse range of applications in the sensitivity, if you look in the sensitivity axis, as well as in this, if you look in this x-axis, this is the sensor scale, or the kind of scale that you can measure. So for instance, if you're looking in and zooming in a spatial resolution, you want to really zoom in and look at magnetic features, especially like, the 2D materials that you were, discussing in the, looking at in the earlier talk, you see that there the spatial resolution that we are, trying to understand is in the nanometer to micron scale, right? Whereas if you're trying to measure bulk magnetic field, you don't care about spatial resolution. At some point, you may need temporal resolution as well if you are trying to measure dynamic fields. So there's a lot of different dimensions to measurement of magnetic field, and so obviously there are many different kind of sensors. I want to just highlight a couple of sensors that have been very interesting in the in trying to measure two very interesting applications. One is if you have a spin and then you have proteins next to it. These
spins can couple to the proteins, and through the dipolar coupling, you can, get back and reconstruct the protein structure. Now, most of the proteins in human body or in mammalian cells actually cannot be crystallized. And so this is a method by actually trying to understand the crystal structure of proteins or a structure of proteins. Now, obviously now there is a sort of a push towards miniaturization, because if you really want to use it as a practical technology, you cannot have like tabletop kind of devices. You need to push towards it. And so one of the sensors that NIST came up, this is NIST in USA, that came up with is this atomic kind of a vapor. And similarly, you have counterpart solid state sensors. Now, at the heart of all this magnetic field measurement is essentially a two-level system, a very textbook system that we use, which has a ground state and an excited state, which you can represent on a block sphere. And what you do is you get the qubit, and in this case, this is a qubit that you sort of create the state as a superposition. Let it feel its environment, and from its environmental feeling, which is essentially a phase that is picked up in as a relative difference between the 0 and the 1 state, you essentially can then measure its environmental effects. And in this case, we are trying to look at magnetic field. Now, there are various different kinds of two-level systems, as we are aware of, photons, atoms, and spins. And today I'm going to be talking to you about spins. So, diamonds. So you've all seen very bright and nice shiny diamonds, which are, of course, the clear ones, and colorful ones are very expensive diamonds, as we know. And actually, if you look at the spectrum that diamond covers, it goes all the way from, black diamonds to green diamonds, and covering all the visible range pretty much. And this happens because you have defects in them. So this is the standard way in which this the diamond gets its color, is that if you have any other atom substitute or form an interstitial defect within the carbon-carbon bond, then it has a spectral range which covers almost all of this. Now this can be and primarily yellow is the most common one, because it is actually the defect is actually because of nitrogen. And nitrogen, as you know, is most abundant in the Earth's atmosphere. So when the carbon or the diamond is actually forming, the nitrogen can seep in, and this nitrogen forms this defect, and this gives it this very nice bright yellow color. Similarly, you have if you have a blue diamond, if you've seen a blue diamond, that's because of boron as the defect. The pink one is the one that is of interest to me. The pink one is, and I'm sure you've heard about the pink star, the famous pink star diamond, and that's actually because of the nitrogen vacancy defect that is sitting there. So the pink star diamond this is the image of the pink star diamond. This has a lot of envy centers in it, and I'll tell you what. So this is the lattice of the diamond, which is a crystal. So you have nitrogen as a substituted atom in the lattice of these are all carbon atoms, and then if you have the substitution of nitrogen along with a vacancy and an additional electron, it forms what is known as an Nv- system, and this is the important system for us. And this is like as if you can forget the rest of the carbon lattice altogether and just focus on this Nv-. It forms a deep defect, and it behaves exactly like an artificial atom. So it's an atom that has a ground state and an excited state, and some very special properties at room temperature. So it's a room temperature qubit. It can be optically polarized, optically read out. So if you were working with spins, you need to polarize it, because you need to create a very nice high fidelity zero state. So that is the meaning of this optically polarized. And then you can read out the states. You need to read out. If you're doing the measurement, you need to read out the state. So reading out is very important. In this case, we optically read out. And how do we do it? We shine green laser, and out comes red fluorescence. So we pick up that red fluorescence, and if you actually zoom in with a confocal microscope, which essentially allows you to look into different layers of the diamond sample, you can actually see these bright spots. These bright spots correspond to these individual defects. And within a spot, you can have one or many defects in there. In the example that I'm going to show you now is defects where we don't look into these individual defects, but they're all many defects that we are working with. Very high density of defects, in fact. So let me give you some examples of where they can be used. So a high density sample which can measure the magnetic field, these can be used in various different applications, such as, for example, looking at vortices. Now, you were talking about superconductors, and you essentially want to understand the electron-electron correlations and also map out the electron-electron correlations. Here we have a technology which can actually zoom in to a material, a superconducting material, and visualize the movement of vortices. So this is a technique by which you can actually look in and quantitatively identify what is the magnetic feature, what is the current that is forming, and all of this. And similarly for graphene, if you flow current, you can actually look into a device and understand the current flow that is happening inside these materials. Now, another very interesting thing that has come up as an application of this methodology is to look into this sort of current flowing structures. As you know, all of our chips, everything has current in them, right? So they are essentially devices that have various wires which have currents flowing through them, and these currents will obviously have magnetic field associated with the current. And so, but now if our phone stops working, you essentially just put it on the side and you buy a new phone. You don't really try to investigate what is happening to your phone, right? So there are no techniques, in fact, to investigate a chip once it has already been fabricated. So what we are trying to develop is actually a methodology for looking at these chips in a non-destructive fashion, so that you can, by mapping the magnetic field, you can actually find out if there is a flaw in the device after it has already been fabricated and packaged. So this is very important. So this is a kind of application that a qubit can actually perform. Now let me give you a summary of how this measurement is done. This is the electronic structure, level structure of the artificial atom that we are talking about. And this is the NV center. This is the ground state. So in zero field, the plus and the -1 levels are actually degenerate. So it's a spin triplet in the ground state and also in the excited state. There is a metastable state here. So when you shine green laser, what happens is that it emits red fluorescence. Now this fluorescence is actually dependent on the spin state of the NV center. So if it starts out with 0, then the fluorescence is much higher than if it were to be started from plus or -1 level. So this gives us a way to read out the spin system optically. Now, how do we do a typical experiment? We polarize all the spins to the ground state by just shining green laser. If you just use a laser pointer, in fact, it works very nicely. You can create 0 state, and then you apply a microwave pulse, which is, you just sweep the microwave frequency, and as you sweep the frequency, you trace out this sort of a curve, which is known as the optically detected magnetic resonance. Now, this dip happens when, as soon as you hit the resonance between 0 -1 and 0 +1 levels. Now, suppose you have a fluctuating magnetic field around it. What happens is that this line actually moves. And since this is an electronic spin, it is automatically calibrated with this gamma factor, which is essentially 2.8 megahertz per Gauss. So every time it moves because of 2.8 megahertz, it is because of 1 Gauss of field that is in the neighborhood. So what you see is that this is a calibrated shift. It's an automatically calibrated system. And so you can measure the magnetic field with very high precision. In fact, here the kind of sensors we are talking about have a sensitivity of almost about a picotesla level sensitivity. Now, standard kind of electronic spin control is very much possible in this system. And so what you can do is then apply, the standard ESR protocols, for instance, Ramsey or Rabi kind of protocols. So when you do a typical optically detected magnetic resonance, you will see not just one resonance, but you see 8 of them, in fact. And 8 of them come because of the 0 +1 and 0 -1 from 4 different classes of NV centers. Now, as I showed you in the previous slide, the carbon that is in the lattice, so nitrogen can be in 4 possible orientations. And in a standard sample, you have almost equal probability of all the 4 classes of NV centers. And so you get 8 lines from this. If you zoom in a bit more, you get the hyperfine splitting because of nitrogen, that is nuclear spin that is present. So you have an electronic spin interacting with a nuclear spin, and you get a hyperfine interaction here. In this case, it was an N15 sample that we have. So you can see beautiful hyperfine splitting here. And when you sit at one point here, do a textbook Rabi experiment, which means you're driving the spin again and again, and you see the very nice Rabi oscillations that come up here. You can do, the next step is to do a Ramsey and essentially to split this by 2 pi over 2 pulses, like just in this, on the block sphere, you can see you apply a pi over 2 pulse, let it precess, and you see the very nice precession here. And as it picks up the phase, this phase essentially carries the information of its environmental magnetic field. And this is the best way to also measure magnetic fields. You can do much more, higher level of phase control and pulse control, and you can do many different layers of experiments with this same system. Now, I want to really quickly go into the application that we are interested to, carry out, given that we can measure magnetic fields at the picotesla level. Currently, of course, not at the picotesla level in my lab. We are at about 120 picotesla. But there are still some applications that we can already move ahead with this sort of imaging. So now imagine that you have, so this is an image of atomic magnetic field sensors. So essentially in our brain, what we have is a whole network of neurons. Okay, neurons look like this. It has a little bit of a cell body, and then they are connected by these wires, which are called axons or dendrites. Okay, and these exchange electric potentials between them. And through this exchange of electric potentials, all our activity actually happens. So when we are thinking or working or doing anything, we are essentially exchanging axonal potentials between these neurons. And as you can imagine, if you have an electric current flowing in a wire, you have a magnetic field associated with it. So that is exactly what we are trying to measure. Of course, to zoom in and identify where those electrical pulses are actually originating. So the goal is to be able to locate those neurons so that you understand how the current is flowing in these different channels, and then correlate it with the kind of stimuli that you're given to it. Okay, so that is the main holy grail goal of this field, to develop a technique so that you can image the neurons and interaction of these pulses. Okay, so of course, we don't have a single neuron there, right? You have a whole in fact, a very dense network of neurons. So the idea is to really zoom into those neurons, but at the single neuronal level, so that you can identify the source of these stimuli. And this is exactly what it would look like if you were to imagine like a neuronal cell culture. But of course, I'm a physicist and I don't work with biological cells. So we decided to mimic those kind of neurons. And how do we do that? With a current. So essentially, these are current carrying wires. So we imagine that this is going to be our network of neurons, which is essentially a bunch of current carrying wires. And I'll tell you why we chose this specific design. But let me give you an idea of where this inspiration actually came from. So when I was in Harvard, in MIT, our colleagues at Harvard actually measured the neuronal potential, or this is actually a real measurement of an axonal potential of a live C. elegans worm. Now this worm is very dumb. It has only one neuron, which is extending all the way across the body. And so it is a very excellent test bed for understanding whether you can ever measure a neuronal signal or not. So what you have is a diamond NV center, which is sitting underneath this worm. And as this worm is being poked, every time it has this, one stimuli that goes by and has a sort of the axonal potential. And this is the potential that is measured by an NV center, diamond magnetometer. Now, of course, as you can see that the levels are very low, well underneath the Earth's magnetic field, and it's only a single neuron. Now, of course, we want to extend from here to here and ultimately into this volume. So it's a very big and very challenging problem that we are looking at. Now, so we decided to make these sort of mimicked wired structures. But let me give you an idea of what the real problem looks like. The problem is essentially this. You have a network of neurons which are exchanging electrical pulses between them. You want to measure the magnetic field that comes from this network of neurons. But remember, what we have is a sensor that is sitting underneath this sort of a cell culture. So that means the magnetic field from this entire cell culture is actually going to come to this field, which is a vector sum of all the magnetic field. So what we have to do is not just measure the magnetic. First of all, it's a measurement is going to be very hard because it's a very tiny amount of magnetic field. And then you want to reconstruct back the magnetic field in 3D. So it's a very difficult problem. So it's an inverse problem also has to be developed. And along with it, the measurement technique also has to be developed. Now we are working on both these levels, and I will not have the time to discuss all the details of it, but I'll give you a glimpse of the kind of things we are doing with this sort of these two problems at hand. So here is how we mimic our neurons. A very simple structure, which is essentially a large head and a long tail. So just to mimic the neuronal structure, you have a large head and a strong tail. And so you have this spiral structure. We chose this very carefully so that it is easy to fabricate. It's a 2D layer, and then we can stack layers on top to make a 3D structure. So that's how, and it actually took us a lot of time to come up with this very nice design so that you can get also the field ranges in the correct range that we want to use for developing the device. Okay, so given this, our main goal was to look into the magnetic field coming from these wires that carry current. And we built a very nice device and completely, sort of a tool to look into the magnetic field images. And I'm just going to go into the images themselves. So what you can see is as you flow the current in the wire, you can look at the magnetic field that comes out from a wire. As you know that the magnetic field will be circulating, so that means it will go from plus to minus. And what you see in this color scale is essentially the blue part of the neck. The red part is the minus to the plus range. So it's going in circles along the wire. And you can recreate both the Vx, Vy, and Vz fields of this wire. Now, important thing to note is that neurons are electrical pulses which are time dependent. So far in the world, until we started working on this problem, there were only static imagers in magnetic field. Now we came up with like, okay, well, we have to measure the magnetic field from a neuron, then we have to have the temporal capability as well. So we came up with an interesting and unique design where we started using lock-in detection techniques in wide field images. And this is the first time we showed actually that you can look into time dynamics of magnetic field in wide field. So across an area of 200 micron plus 200 micron with a spatial resolution of 1.5 micron, you can have a temporal resolution of 30 milliseconds. So you can actually really look into the temporal changes in the magnetic field. And not just that, you can also look into the harmonics. If you send in a square pulse, you look into the harmonics of the field itself. So we did that and we looked into a single coil, and then now we are interested in also looking into the models. Now I'm going to skip through all of this, but one interesting thing I want to show you is that when we did the complete simulation of our system, we found that the axon hillock has much higher field than the rest of the neuron itself. And so we decided to make some, theoretical modeling and predictions, and we developed some matching pursuit kind of algorithms. So as part of the algorithm work, we did some modeling, and we found that if you have a neuron that is spiking at about 1 millisecond apart temporally, then using our method or techniques, we will be able to reconstruct back this image. We are now extending this work into 3D, and I just want to show you this video. So this is a real-time image of currents that are flowing in this kind of a structure, which is a 3D structure. So it's a stacked layer of microcoils, and you can see as you send spiking currents, you can map out the image of the magnetic fields. Now, immediately, as an application for even a condensed matter system, if you have, say, a superconductor and you want to look into, this, the dynamics of vortex flow in a similar kind of a structure where you have current flowing through a superconductor, this is also an equivalent technique. And in fact, this is what we are building for fundamental science as well. So in our lab, we have started to convert the system from room temperature into low temperature, as well to specifically understand if you have similar kind of devices which are not just current carrying simple wires like this, but very interesting materials like 2D ferromagnets, or any kind of other class of quantum materials, then these are the kind of things we will be able to study. So given this, we started looking into different kind of optimization techniques of understanding how the imaging, etc., will work. So with that, I will sort of, in a brief amount of time, I've sort of given you an overview of the kind of things we are doing for developing this quantum diamond microscope, which is able to image magnetic fields in the micron scale. And we are now trying to extend going from 2D to 3D imaging, which is a very big challenge in the field. And then applying this to not just, of course, the kind of problems which are applications, but also to fundamental science. So of course, I have to thank the people who have done all the hard work. Madhu really built the setup. Shishir and Anuj did all the hard work of the measurements itself for all the work that I've shown you here. Thank you very much for your attention.
For a very interesting field of research. So you can take some quick questions.
Thanks for a very nice talk. Just curious, I'm not aware of this space, but are there experiments of any to quantify or measure quantum Hall kind of space, or like, I mean, it would be exciting to look, because there it's like electron mobility is always a pain. But
Yes.
will your technique help?
Exactly. So this is exactly what we're going to do now. So we have just set up a low temperature system in our lab, and we are in fact building the same wide field microscope for a low temperature system. So what I showed you are all measurements done at room temperature. We want to extend this, and exactly the kind of experiments that you're talking about, we will be doing this. But of course, in the world that we give you the global status, there are a few groups that are working. For instance, there's a group in Basel that is working, there's a group in Australia that is working, and of course, Harvard, a couple of people are doing this sort of work. So they're really the pioneers of this field, and they have been working in different kind of, but mostly it's all 2D imaging and static imaging so far. We are extending that to really the temporal version.
Just a quick follow-up. Can you go to 1D? Just quickly, because can you measure if I have a like a 2D surface state, that's okay. But if I have a 1D edge state,
Yes, we will also be able to, yes.
I mean, I'm just curious of the technicality there. Sorry, but it's like and we will still have some resolution, right? Can you still tap into 1D?
Yes, we can. So the technique that I've shown you here is a 2D imaging system. So basically, it's like an analog of a standard microscope, but we do magnetic field microscopy. But what you can also do is you can have a tip with an AFM tip, if you are aware of an AFM. So AFM is the standard scanning technique. So if you replace that AFM tip with an NV tip, you can actually really image at 5 nanometer spatial resolution and really look into the maps of all these different, edge states as well. The kind of resolution that we can hit here are about 250 nanometers, but you can combine both scanning and wide field as well to get these kind of issues. Yes, sure. I mean, you can ask me. Yes.
Just one comment, that in living systems like in microbes, biofilms, microbial communities, electrical signaling has been discovered in a paper in Nature. It appeared in 2015.
Yes.
And another thing that J.C. Bose long back said that there is electrical signaling. There is no neuronal network in plants, but electrical signaling exists.
Right.
And now there is experimental proof of electrical signaling. I was wondering that probably your method can be extended with magnetic field mapping, etc. Some indirect way of proving that electrical signaling is going on.
Yes, actually, in fact, the techniques I have shown you, there is a very recent paper a Japanese group has done this. So they've actually done a cardiac encephalography on heart of a rat. So they have actually detected electrical signals as well as magnetic signals with this NV system itself. So this is very much possible to do. So people have already shown these kind of things.
Thanks, Kasturi, for nice job. And just a name question in anything in this imaging, you also doing classical, using classical. So any theoretical results have been established that, okay, this is the benchmark, if my imaging is better than this, fidelity, then only a quantum advantage, you can say it is established. Any theoretical results in literature is there?
There's plenty of literature for, how you can really push this system to the actual quantum limits. Now, here we are using the spin as a qubit, of course, to do the measurement. So in that sense, this first world quantum. To really go into the second world quantum, which is really harnessing the interactions between the spins, you have to have a little bit more complicated, system assembly. Now, that's not very easy to apply it for imaging. So it's a little bit tricky there. We are thinking in those lines as well. But, to go there directly to really say I can push it to the Heisenberg limit, that's very hard actually in these kind of systems for imaging, for instance. Yeah.
Maybe discussions over.
Sure.
Thank you very
Thank you
much.
very much.
Wonderful talk.
I request our session chair, Professor Rajiv Mitra, to hand over the memento to Dr. Kasturi. Now, before the next talk begins, I have just a small announcement. So this will be the last talk of this session. Please don't leave immediately after the talk. We will have a group photo here. So please don't leave after this talk.
Okay, so I'm very happy to introduce our next speaker, Raka Dasgupta, who has been a student of this SNBOS Center. She did her PhD from this center working with JKB, and now she is a professor at the Calcutta Physics Department, Calcutta University. Her area of research encompasses condensed matter theory, statistical physics, and things like that. Okay, so Raka.
So good morning, everybody. My sincere thanks goes to the organizers, Tom Stevie and her team for inviting me here and also for arranging this wonderful conference. As Ravitra just said, I was a student here. I did my PhD from SNBOS. So every time I step in here again, it's like coming home for me. So thank you again for giving me this opportunity. And I'd like to start with a bit of personal recollection. So back in 2010, I was a PhD student here. And in that year, DSP had sent us a directive that the Science Day has to be observed under the theme Women in Science. So someone from the administration here, I don't exactly remember, maybe Shunish Babu, he told me that why don't you design 5 or 6 posters on that theme? And I'm very ashamed to admit that back then, I didn't know the names of Purnima Sinha or Vibha Chaudhuri and all the women we had here. So all my posters revolved around the works of Rosalind Franklin, Sophie Germain, Amy Noether. And also I tried to gather some statistics. So what I did was I visited the websites of different universities, institutes, both in India and abroad. And I counted the female sounding names and computed the ratio. So those were the tables that I showed back then in those posters. So that was something interesting. So I had a preconceived notion that India being a developing country, we have this gender gap. Then I was very shocked and surprised to find that in the first world countries, the ratio is even worse. So I thought, okay, at least we are doing better in terms of the ratios. And I think the game has changed since in the last, it is 2010, so in last 14 years, I think the game has changed by substantial amount. And I sincerely thank our academic foremothers for that, who are the trailblazers, some of whom are here involved in this conference. So thank you for making our journey so smooth and easy for us. Thank you. So here is the brief storyline. So just I'll be talking about a little bit of S.N. Bose and his connection to the undercooled atoms. My work on Rydberg atoms, and also I'm very happy to find that today itself we'll have another talk from an experimentalist, Sanjukta Rai, who works on Rydberg atoms, and she in fact actually I had her name since I was a PhD student here, so she herself is associated with the first Bose condensate that was produced in India. So I'm very eager to hear it from the horse's mouth. And so I'll be talking about, I'm a theorist, so I'll be talking about some statistical aspects of Rydberg atoms on the lattice, the kind of phases that emerge, and so on. So this is a story that we all know, but again, it's a story that's worth revisiting every time we talk about. So we are celebrating 100 years of Schopenhauer's work. The letter he sent to Einstein, the way Einstein extended his ideas, and the way we got our Bose-Einstein statistics. So one of the most spectacular consequences of this theory was that if you pull a system of bosons below a certain critical temperature, you will have all bosons coming down to the lowest quantum state, and a new form of matter, Bose-Einstein condensate. Again, back then it was just a theoretical prediction. Experiments came much later. And although this poem of Richard Feynman is not about Bose condensates, still I feel that these lines actually capture the true spirit of the science. So deep in the sea, all molecules repeat the patterns of one another till complex new ones are formed. They make others like themselves and a new dance starts. So I'll be talking about some parts of this new dance. So again, just the timeline that in 1995, the first Bose-Einstein condensation was achieved experimentally. And in 2003, the first Fermion condensate was achieved from the lab of Deborah Jean. Since this conference is celebrating women scientists, so I feel it's appropriate to highlight Deborah Jean's work, because one of the most pioneering works in undercooled atom experiment came from the lab of a lady, and it's her untimely demise that has robbed us of most such achievements. And why undercooled atoms? I think Indrani has covered it in her talk as well. So when you go down to a very low temperature, it's the quantum effects that dominate. So you essentially have a new shade of the game. So the classical effects are not there anymore. And you have a much better controllability. You can tune the atom-atom scattering length. You can control everything about the atoms. And a game changer is the invention of optical lattices. So you have counter-propagating laser beams forming something like a lattice, and the lattice geometry, the lattice dimension, the way one atom can hop from one side to another, the on-site interaction, everything can be controlled. And that is how you can actually mimic traditional condensed matter systems, nuclear systems, everything. The way Indrani was talking about a toy model being replicated by ultra-cold atoms very recently. So this actually gives you a very good test bed for traditional branches of science. You can build the models. And this is the Rydberg story. So what are the Rydberg atoms? So this is that atoms in states of high principal quantum number n. So basically they call this, so this is a very crude classical picture which should not be here actually, but I just put it for simplifying things. So you have one or more electrons pushed up to high quantum number. And so you have something like they call daddy atom. So instead of this atom, effectively your atom becomes this big by several orders of magnitude. And now what happens is if you have two such atoms in close proximity, if you excite suppose you have a two-level system, you excite one atom to the excited state. What happens is for the second atom, because of the strong dipole-dipole interaction, the upper level goes up. So for the second atom, it is difficult to climb the stairs up because now the roof has been raised. So what you have is called Rydberg blockade, which means for two atoms in close proximity, if one atom is Rydberg excited, there's a high chance that the second atom won't be Rydberg excited. At least the probability will be very less. So that is the blockage that has been talked about in Rydberg systems. In our system, what we are thinking of is, I forgot to say that, the effect of Rydberg blockade that has been studied both theoretically and experimentally. When they treat the system like a lattice, that you have several atoms that could be Rydberg excited, scatters, you imagine that as if there is a lattice, and then you study the subsequent dynamics. And also this blockade is closely associated with creation of quantum entanglement. What we assume here is you actually have an optical lattice. You dump the atoms in that lattice. So what you have is a cloud of atoms in each of the traps, each of the lattice sides. And there is this Rydberg blockade working. So this is something like this. You have a strong blockade up to a certain blockade radius. And after that, the interaction just diminishes short. So the idea is something like that in one of the wells, if one atom is Rydberg excited, no other atom can be Rydberg excited from the very same site. As for the nearest neighbor site, one atom may or may not be excited depending on the Rabi coupling between the ground state and the excited, also the detuning, etc. So basically, you have essentially we call super atoms. So either a state where all the atoms are in the ground state, or all the atoms minus one are in the ground state and one is in the Rydberg excited state. So if all the atoms are in the ground state, we call it the system ground state. If one atom is Rydberg excited, we call it the system excited state. So we are not talking about the atomic ground state or the atomic excited state anymore. So it is the overall the collection of atoms that can be in the ground state or can be in the excited state. And this, since there are many particles on the same site, you have the on-site interaction, the one like the Hubbard model in the atomic limit. So basically, we are talking about the influence of this on-site interaction, which again can be designed and controlled by changing the trap depth or maybe by applying a feedback magnetic field. So how that can result in different phases in the system. So this is the Hamiltonian. So basically you have this detuning between the ground and the excited states, a Rabi coupling, a laser coupling between the excited and the ground states. The on-site interaction results in a form like this. So if all the atoms are in the ground state, you have a contribution to n into n minus 1. If it is the excited state, this is something like this. And this one is the Rydberg interaction. The V, this is the interaction strength. And we study the non-equilibrium dynamics, assuming there is noise in the form of continuous emission from the excited state to the ground state, dissipation is there. And when we find that there emerges two alternating sublattices. So what we mean is that for one set of parameter values, you have something like a uniform or a paramagnetic phase. So the Rydberg excited states can be anywhere in the entire lattice. In some parameter regime, on the other hand, you have something like the Rydberg excited states be occupying only one particular sublattice. So this is what an ideal case, that all the atoms in one sublattice are in the ground state, where all the atoms in the other sublattice are Rydberg excited. But even if we cannot reach this limit, there could be other ones where at least the majority of the Rydberg excitations play for one particular sublattice. That we can call the antiferromagnetic phase. So we study the system dynamics under mean field approximation. We define omega j is the population difference between the ground and excited state of one particular site. And this is the order parameter we construct, meaning if the Rydberg excitations are evenly distributed among two sublattices, your order parameter is 0. If all the Rydberg excitations are in one particular sublattice, like the picture I just showed, it will be 1. And for all other configurations, which are antiferrometry, but not exactly 1, there will be some fractional value of theta. So this is the particle dynamics looks like. So for some set of parameters, you have this uniform phase or the paramagnetic phase, we can call it. So the omega values from two sublattices fall on top of each other and you have a single line. For a different set of parameter values, you have something like this. So one sublattice red corresponds to one particular sublattice and blue for the other sublattice, and there is one definite gap among these two. And there is one curious third phase where you can actually have, which is a subclass of this antiferromagnetic phase, but with some oscillation. So you have a difference between the omega values, but the values are not fixed. They keep changing around some mean value. We call them the oscillatory phase. So this is our phase plot. This is how the order parameter varies with the on-site interaction strength. So we keep changing the on-site interaction. And these pictures are for different Rydberg interaction values. So we gradually increase the Rydberg interaction value. And we have something like this, one flat uniform region, then a drastic rise to the antiferro region. Then you have this curious oscillatory region. So this consists of small oscillations around here. And then again, you have this flat uniform or paramagnetic region again. And the same pattern follows for all these phases, all these phase plots for all these B values. Only with an increasing Rydberg interaction strength, the area of this oscillatory phase in the phase plot, this increases. So again, these are all these plots shown together. If theta equal to 0, you have this uniform phase. Theta not equal to 0, you can call it this antiferro, or even you can call it ferrimagnetic phase because it's not exactly 1. And here you have this oscillatory region. And we wanted to probe on we wanted to explain how this kind of structure comes out. So when you have a positive U, what happens is you tries to excite a particle in the, suppose one particle is excited in site A. In the site B, Rydberg blockage tries to prohibit the excitation. But since this interaction is repulsive, pulling one particle up here will reduce the energy. So basically having a positive U works in the opposite direction of the Rydberg blockage. So the Rydberg blockage is kind of weaker. So basically that is why in the positive U regime, you have this oscillatory thing. The antiferromagnetic nature is not robust anymore. The atoms cannot, the system cannot make up its mind whether to stay in the ground state or in the excited state, and you have this continuous to and fro oscillations. And if you have large positive U, that means basically no effect of the Rydberg blockage. So something like BOSEStat model in the zero hopping limit. So that is what you get here. And if you have a negative U, meaning the on-site interaction is attractive, then what happens is this, if this particle is excited, the excitation of this particle in the nearby site is prohibited because of the blockage. And also the effect of this negative U also the same, that it also tries to prohibit this excitation. So the negative U actually enhances the Rydberg blockage. So you have a more robust antiferromagnetic regime. And again, in the large magnitude of U limit, no particle can climb up the ladder anymore. So you actually have all the particles in the ground state, which is uniform phase. And we wanted to inspect the origin of this, especially this oscillatory and the antiferro phases from the nonlinear dynamics of this system by doing the stability analysis. So what we find is that here is this stable uniform fixed points, which corresponds to this uniform phase. From these points onwards, they become unstable and the non-uniform fixed points become stable. So we have this non-uniform antiferromagnetic region. In this region, all these branches become unstable. That is why you do not have either a stable uniform or a stable non-uniform phase. You have these nasty oscillations. And finally, here you again find this stable uniform fixed points and the uniform phase. And we also plotted the correlations. So we just did a small simulation and of semi-classical multi-color simulation of the. So this is kind of equivalent to the Ising system. So you can think of the round and Rydberg excited states as the upspins and downspins. So you can do a multi-color simulation. So what we found is that in the antiferro phase, you have this kind of a zigzag nature of the correlation. So for all the even sides, there is positive correlation. All the odd side difference, there's negative correlation, hinting at this antiferro structure. For the uniform or paramagnetic phase, as expected, the magnitude of correlation is very small, nearly zero. So essentially, the correlation is kind of absent here, and that is why you have this paramagnetic kind of structure. What happens in this interesting oscillatory phase is that you have this antiferro correlation, only the magnitude is far lower. So you have antiferro correlation, but the correlation is not strong enough to hold the particles fixed at ground state or the excited state. So that is why you have this kind of oscillatory dynamics. Some particles come down, some particles go up in the course of time. And we wanted to look at the phase transitions from a purely static perspective. So what we saw is that from this uniform to antiferro phase, there is a continuous transition. And on the other hand, from this non-uniform to uniform phase, there is a discontinuous transition. And we wanted to check whether any scaling relations can be found along this continuous transition. So what we found that order parameter follows a mathematical structure like this, where UC is the critical value of the interaction strength where this phase transition occurs. And initially we had expected that the beta will be some constant which will reflect universality. But what we found instead was that beta is a linear function of the Rydberg interaction strength. So beta is not a constant. If you increase b, it goes like some alpha 1 b plus alpha 2, this kind of structure. So this probably falls into the domain of weak universality that we found that in case of weak universality, not all critical exponents, some of the critical exponents show universality and the others show a continuous change. They change continuously with the external parameter values. And we are yet to check whether some super universality emerges, meaning although the individual exponents change as the parameter changes, their ratio remains constant. But since at this point we have only beta in hand, we cannot check for other critical exponents, but this is on our agenda. And just as the kind of future directions one can have, of course, this kind of antiferro structure, this Rydberg blockade that results in quantum entanglement, which can find applications in metrology, designing quantum gates. And from the pure static perspective, I'm curious to see the kind of the criticality or universality that emerges in the system. So this basically is kind of a synthetic Ising model, the Ising model in the transverse field with dissipation and with this additional Rydberg blockade kind of constraint. So for acknowledgements, so this is all I had to offer regarding acknowledgement. Of course, I acknowledge my department and PhD SCRB for the CRG grant. My PhD student who is working on this particular work, she is supported by PhD Inspire grant. And although the work I presented here is entirely Shubhacha's and my work, we are talking with Anirudh, who is also an student of our department. And only yesterday, I think there was a talk going on regarding the job prospects. So Anirudh, who is right now quantum computing engineer in NIT, but he is just in his individual capacity and curiosity, he got associated with this work, and currently what he is doing is implementing a 1D simulation in Pascal. So the results I showed was in field, so more applicable for 2D or 3D, not for 1D. So for 1D, we asked him to simulate the system. And although the results are still half-baked, so I'm not showing it here, but he got signatures of this transition from uniform to antiferro phase. only difference is that for us, the pattern is for sharp here. What he got was something like more spread out pattern in the face plot. So these are my students. So Shubhendu, Shubhecha is the one who worked on this, Madhumita and Obhinobo. So I can boast of healthy gender ratio in my group. And again, my tribute to the ones who gave us wings, who built the sky for us. And this time I won't forget the names of Purnima Sinha or Vibha Chaudhary, Athena Chatterjee. And thank you all for your patience.
So we can take one or two questions. Yes, okay.
So what is the paramagnetic state and then the real type of ordering? The first is like a gas, the real type of system has long range order, it's like a crystal. But have you found any quantum spin liquid type relations in this arrangement of Rydberg atoms?
What kind of relation?
Quantum spin
No,
liquid.
I mean in terms of what parameters?
The Rydberg, you show
Yes.
the patterns
Yes.
using Rydberg atoms.
Yes.
They are ground states and excited states.
Yes, yes.
So you said that there can be a paramagnetic arrangement and then
Yes, but I mean by paramagnetic, I mean if you talk in an
it's analogy.
analogy, it's analogy.
Mimicking a condition.
Analogy, and yes, you can think of it as a gas liquid system as well, so.
Quantum speaking, we have non-trivial, very interesting operators which will have a non-zero expectation value. They will some kind of long range.
I see. But I think, I mean, at least in terms of correlation, there is no long range order, so.
They conventional long range order is missing.
The conventional.
Different sound. Operator
Okay.
which will have
I
a non-zero
see.
expectation value.
I see that, I haven't seen that, but because the correlation was, I mean, this showed no long range order, so. That is why I could not even find the, I mean, the other exponent new, because but if we can find some, in terms of some other operators, maybe that will be helpful.
Thank you, ma'am, for the management. We're talking about the resource states, but we do have some finite lifetime, so there will be some decoherence in the system. Sure. So you mean that if it's the result in paramagnetic and paramagnetic, whatever you have considered.
Sure, there will be beforehand. So the system we are thinking of it, I mean, it's not exactly an open system, but one way open meaning you can come down from the excited state to the ground state. So there will be continuous case up to the ground state. But we are not allowing escaping the atom to outside. So in that way, it is a closed system. But certainly there will be decoherence. So I forgot to mention that on the phase plots is for some particular time. So I have to fix the time and compare the phase plot. So if I go beyond that, difference will start saying.
Our comment for that question is that in Rydberg atoms, the lifetimes are very long.
Very long.
For example, if you see the lifetime of a first excited state in rubidium, it's like 28 nanoseconds. And for anything of 100, it could be like 1 milliseconds. So this makes the Rydberg atom, a very coherent system with a long lifetime. So that's why Rydberg atoms are so promising for, doing, quantum simulation of many-body physics as well as quantum computing.
And then entangles that will survive for much longer.
Exactly, like quantum entanglement, the coherence is like exceptional as compared to the other.
Actually, I mean, the simulation is also important. So what happens if I take a very last time, then I mean, everything gets, that even the phase structure gets changed because of the difference.
So thank you, Doctor. We talk. All the speakers of this session for I wonder if I pick it and.
So now I would like to request our director, Professor Tanushree Shahadas Gupta, to please hand over the memento to the session chair, Professor Rajiv Mitra.
So this brings us to the end of the morning session for this conference. Now, as announced previously, we will have a photo session. The rain has stopped, so we can go down. And just at the entrance of this building, there is a good area. We'll have the photo session there. And then we will have the tea break. So I think we can meet at around, there are 3 talks after this session, 20 minutes, 11:40. 11:30 was the scheduled start, so we'll delay it by 10 minutes, 11:40. So we will head downstairs. Okay.
Timer 25 minutes. 20 plus 1.
We can know that.
जब हम start होते हैं And would you like to use this for headphone one because with the close the
দেখুন আমার কি বলছে কিন্তু আমার কিছু করার নেই না মানে ওনারা চেষ্টা করছে কিছু করার নেই ওইটা নড়ছে তোমার ওইটা চেষ্টা হচ্ছে ওনারা আমার চেষ্টা করছে
Welcome back, everyone. Now we are going to start the post-week session of the last day of the conference on women in quantum science and technology. And I request Professor Mike from Methodist Center to lead this session.
So, welcome again. So, in this session, we have three fantastic talk by three scientists doing exceptionally good research in their respective field. So, our first speaker is Dr. Peter Kochar she is assistant professor at IIT Kharagpur. Dr. Kochar did her PhD from IISc and then postdoc from Rice University. Research area is mainly nanomaterials, and she have obtained several awards. Her Women Excellent Award means Medal for Young Scientists, Nancy Young Scientist Awards. And today she is going to talk about this van der Waals epitaxial growth of 2D, quasi-2D material, and it's long title. So it is 25 minutes, 20 plus 5.
Hello all. I'm Dr. Vidya Prachar and I work at Material Science Center in IIT Kharagpur. So in the morning we had some wonderful talks about magnetism, and then we heard about electronics, interesting aspects of 2D materials. So the topic of my talk will be basically growing these kinds of interesting quantum materials using a special type of epitaxy which is called as Van der Waals epitaxial growth. And I will be focusing on growth of 2D and quasi 2D materials, and I'll touch upon what are the interests for these materials in optoelectronics and spintronics. So, first of all, I would like to thank all my group students and the funding agencies who have helped me in setting up this lab. And we actually work on 4 different verticals. So we work on quantum materials synthesis with owners on 3D materials. Then we fabricate devices. Then we study light matter interactions. And then of late we have been looking at quantum transport phenomena as well. So the topic of today's talk, the first part will be based on quantum material synthesis. And for that, I would also like to acknowledge the work of one of my former MTech student who has been instrumental in studying some of the quasi-2D materials. And towards the second part, I will also talk about light matter interactions. So the top outline will be this. So I will introduce you to the epitaxy of 2D and quasi-2D materials group. Then I will take 2 specific systems which we have been working on in our group. So one is a quasi-2D magnet chromium telluride because it has interesting prospects for non-linear magnetism. And then I will talk about these semiconductors like WIC2, where there are interesting optical emission signatures which also is independent upon the substrate on which you grow them. And finally, I will conclude the talk. So let me first explain to you the meaning of the title, Van der Waals epitaxy. So this is a special type of epitaxy, and it is quite different from the conventional epitaxy what one has been studying. So conventional epitaxy, basically you have a substrate and you are trying to grow a epilayer which is having a very small lattice mismatch from the substrate. So if the lattice mismatch is huge between the epilayer and the substrate, then you start seeing these kind of dislocations. You can have misfit dislocations, threading dislocations. So here basically the interaction at the substrate is governed by covalent bond. Whereas now if you take some other kind of materials, for example, you can have, especially these 2D materials, which are layered materials, and you can try to grow these materials on different kinds of substrates, and you can basically grow different kinds of materials despite large lattice mismatch or thermal expansion coefficients. You see that you can still grow very thin layer of 3D materials with very negligible strain. And here the bonding is basically governed by Van der Waals forces. So that is why you coined the term Van der Waals epitaxy. So this is something which has been seen in the growth of a large variety of 2D materials. For example, growth of graphene on hexagonal boron nitride. Then you can have, these kind of transition metal dichalcogenide heterostructures which one can grow. And again, you can see that there is very nice directional alignment of one lattice over the other. And here you see that there are moire patterns that are emerging here. Whereas in the case of these kind of vertical heterostructures that one tries to grow using techniques called as chemical vapor deposition, you see that there is a perfect directional alignment between the bottom layer here, which is MOS2, and the top layer here, which is WSC2. And this is the best way in which you can ensure good interface coupling, which can also result in interesting features, optical emission features like interlayer exciton. But this is not the only thing here. We have seen that the lattice mismatch between the 2 materials are very less. But you can also grow materials with very large lattice mismatch using this, and even with different crystal structures. For example, you can have WSC2, SNS2 vertical heterostructures. You can also grow different types of TMD monolayers on substrates like mica and sapphire.
And what we see is that the 2D material actually rotates on top of the substrate and try to go in a direction where the lattice strain is minimized. So how do you modulate this van der Waals epitaxy? So there are three important parameters one has to keep in mind. The first one is the temperature. So as you increase the temperature, you start seeing very nice directional alignment. And this is because, you know, when you are having nuclei, and if the thermal energy can overcome the rotational barrier, these nuclei can rotate and they can, you know, achieve these minimum energy, minimum binding energy orientations. So temperature plays an important role as well as precursor concentration. So if you have large amount of precursors or the concentration of the precursors is large, you can have small nuclei which are forming, which can easily now orient itself with the substrate symmetry, and you get nice epitaxial alignment. And same in this way, you also have another important parameter, that is the substrate symmetry, which plays an important role in van der Waals epitaxy. So at the end of the day, it's basically between what is the symmetry of the substrate and the material that you're trying to grow. So there are calculations which show that the propagating edge of a 2D material will tend to align along certain high symmetry directions of the substrate. And depending upon that, you can have different orientations which are degenerate in energy. And in this way, you can have different orientations which are possible on a single plane of this substrate. And examples of this one can see when you try to grow graphene on copper 111, or HBN on copper 111, where you have only two orientations here, 0 and 60-degree rotated. But if you try to grow on copper 100, you have other orientations like 30-degree rotation, which is also coming into the picture. And the same has been seen in case of growth of TMBs on large area HBN as well. So now let me go to the first part of the talk with this introduction. So I'm going to focus on a quasi-2D magnet, which is chromium telluride. And first of all, let me introduce to you what is the difference between a 2D material and a quasi-2D material. So when we normally talk about the nomenclature of 2D materials, so these are basically layered materials where you have the van der Waals force of interaction between the two layers. Now, what happens is in quasi and 2D materials, you can have some atoms which are lying in this region between the two layers, and they can give rise to covalent bonds between these two layers. So strictly, this is not van der Waals, but you are introducing a plane of atoms in between and changing the interaction from van der Waals to covalent bonding. So this is, and once you start synthesizing them in very thin layers, then you coin the term quasi-2D materials. So let me talk about this system and why I have chosen this system. Because compared to many of the other van der Waals magnets like chromium iodide, FGT, so chromium telluride has been a system which is shown to be much more air stable. So it's easy to work with this system. And moreover, the interesting aspect is, so if you take CrTe2, it is like a layered material. So you have these layers with which are separated from each other, but you can also tune the stoichiometry of chromium telluride. So what you can do is one can introduce the chromium atoms, or basically you can intercalate chromium between these layers of chromium telluride of CrTe2. And in this way, depending upon the amount of chromium you are able to intercalate, you can have different stoichiometric phases. So you can have Cr5Te8, Cr2Te3, Cr3Te4, Cr3E. All of them are very interesting because depending upon the amount of chromium one can intercalate into it, you can tune the ferromagnetic properties of this material. So this is how we grow the materials in the lab. So we use a technique called as chemical vapor deposition. So where we mount the precursors for the chromium as well as tellurium inside the quartz tube, and then we heat it up to high temperatures. And in the presence of reducing gas like hydrogen, you start seeing that this is getting converted to chromium telluride. So these were some of the initial flakes that we have grown on substrate, which is basically silicon oxide. And we can do XRD and EDAX characterization of this, which basically tells us that this is structure is triangle CR5PA, and also from the EDAX you can confirm that this is having a stoichiometry related to CR5PA. Now the question is, so how can we thin down these materials? That is a challenge. So we tried growing these on different substrates. For example, silicon 100, then we have the sapphire 001, because sapphire is a very good substrate when you try to grow other TMTs like NOS2, WS3, you get really thin flakes, monolayers. But here we saw that still we are getting very thick flakes. Then we took another approach by which what we did was, so we have this graphene and graphite and HBN, which are bulk crystals. We exfoliated these on silicon oxide and then tried to use the exact same growth parameters and grow these materials on top of these substrates. So if you can strain your eyes, you see that there are some light patches on here. It's more visible on HPN. So basically what we are seeing is that we are able to thin down these, quasi-2D materials when we start growing them on parallel substrates. And also this can be, the thickness dependence can be seen in Raman, because when you are having thicker samples on silicon or sapphire, you see that there is a red shift because of the stacking effect. So there is more of a lattice compression, giving rise to a shift of the A1G and the EG peaks. So the question is how we are able to do this, how we are able to thin down these materials when you grow them on these kind of substrates. So basically there are two different types of growth mechanisms that one can look into. So one is called as a Frank-Vandermeer growth mechanism. So in this mechanism, so basically it's like an interplay of the surface energies. So if the energy between the add atoms and the substrate surface is larger than the cohesive energy between these add atoms, then you start seeing this nice layer by layer growth. And on the other hand, if your interaction between the substrate and your add atoms are lesser when compared to the interaction between the add atoms, then you start seeing clustering and you end up in getting 3D islands. So this is exactly what we were seeing. So what is happening is when we are trying to grow these materials on van der Waals substrate, now these van der Waals substrates like graphite, graphene or HBN, so these are free of dangling bonds and also they have atomically smooth surface. So because of that, the surface energy and the interaction energy is less than that of the bare substrate, and we get the layer by layer growth on these substrates. And whereas on the other material like sapphire, where you have a lot of dangling bonds and terraces on the substrate, you start seeing the island growth. So the other question what we asked is, do we really see some kind of epitaxy here? So we have seen that on sapphire we have this kind of directional growth, and we do see that there is a lot of epitaxy, van der Waals epitaxy, directional alignment that is going on in this plane. Now, if you calculate the lattice misfit between the chromium telluride and graphene and HBN, you see that this lattice misfit is huge when compared to that of sapphire. The question is, in that case, what happens? And again, we do see that there is a great deal of orientation that is happening even when we try to go on top of HBN. So now the question is, why? So to understand what is happening, what we have done is we have done high resolution transmission electron microscopy of the chromium telluride, which is grown on HBN and graphene. And what we see is, we see a very interesting FSP pattern. So you have this hexagonal pattern, and around each of these spots, you have satellite peaks. And this is basically a typical way in which one can identify that there is a Moira superlattice. So you can actually see that you can index these planes for corresponding to the chromium telluride and graphene. And what one can see is, so the 220 plane of chromium telluride is basically coinciding with the graphene 010 plane. And if you calculate the lattice misfit for these two planes, you can estimate what is the Moiré period. And from what you can estimate from the theoretical value actually matches with the actual experimental value one can see in TN. So this is the same case with graphene as well as HDN. So the interesting question here is, even though you have a very large, lattice misfit, how the growth is happening. So basically what is happening is when this the epithelium is growing, it is basically rotating itself to a commensurate landscape and trying to grow. And that is why you see these kind of Moiré patterns. So now coming to the interesting aspect of magnetism in these materials. So if you take the chromium telluride material, so the spin moments of the chromium are the important players here. So there are three types of exchange interactions that are possible. So one is the direct exchange interaction between two chromium atoms, and that was basically the antiferromagnetic behavior. And then you can have, the conduction electron mediated exchange, but that is very negligible here. And the third one is basically the super exchange, which is mediated through the chromium tellurium chromium unit, which basically has been shown to be ferromagnetic. Now, the interesting aspect here is, so once you start introducing chromium intercalants, now there are different types of exchange interaction that one can look into. So one is an exchange interaction in each layer of chromium telluride, in each layer of CrP2, so that is J11. Then you can have the chromium interactions between the chromium intercalants, and then you can also have the interaction between the chromium intercalants and the chromium in the in the layer. So basically you have these different type of exchange interactions which compete with each other, and as you increase the amount of this intercalants, you start seeing that there is a canting, spin canting which is happening, and that can give rise to non-collinear magnetism. And we also see signatures of these non-collinear magnetism when we do the squid measurements on the bulk chromium telluride flakes that we have grown. And also we see that there is a perpendicular anisotropy. So anisotropy easy direction is along the z-axis. And we see there are these kinks in the MH loops. And this again shows that there are two different exchange interactions which are related to the chromium in the layer as well as the intercalated chromium. Now, why this is interesting? Because these kind of materials with self-intercalated chromium, it lacks immersion symmetry, and in these kind of materials, there are several interesting factors that can be thought of. For example, the DMI interaction. Then you have perpendicular magnetic anisotropy, as we have seen in our experiment. You have interlayer exchange coupling, and also when you grow them in thin layers, the dipolar interactions are important. And these are all important parameters which can give rise to the observation of fermions in these kind of materials. And in fact, these kind of fermions in chromium tellurides have been observed using Lorentz stem or topological Hall effect, and also by the emission of magnetic bubbles when you do MFM. So these are very interesting class of quasi-2D materials that one can actually start thinking of. So now I'm going to switch topic here, and I'm going to talk more about 2D semiconductors, that is WS2. And so again, using CVD, we have been trying to grow WSE2 on top of different substrates. And as you can see, under the same growth conditions, we get the best growth on top of sapphire. You get very nice monolayers, whereas you start seeing multi-layers on silicon oxide. But the question is, whether this actually shows that this is the best, substrate for growth of WSE2. So this diagram actually shows, this is the optical micrograph here. This is the PL intensity map. This is the PL peak position map, and this is the Raman peak position map. So the ones on sapphire, you can see that it is very non-uniform. There are certain regions where PL is enhanced, PL is quenched, and in these regions, you also see that there is shifting of the PL peak position either towards low energy or towards high energy. And in these regions, you also see that the Raman field is getting shifted. Whereas the samples which are grown on silicon oxide and HBN, these are much more uniform as compared to that of sapphire. So how do we understand this? So these are again several other examples of growth on sapphire. And one way to understand this is because sapphire is a substrate which is having a high thermal expansion coefficient. So we are growing these materials at very high temperatures, and when you try to cool them down to room temperature, this thermal expansion coefficient mismatch will basically give rise to a lot of strain in the system. And this can be seen once the strain can be understood once you start looking at the Raman shifts in these materials. So for example, there are three regions here. The region 3 is kind of the most uniform region. There you see that you have a single peak here, which is basically kind of a degenerate peak between E2G and A1G. And here the blue lines here correspond to the phonon frequencies when you are having zero strain. And now if you look at the other regions, like for example 2 or 1, we start seeing that there are two peaks that are now involved. And you can understand this because now your EG peak, E2G peak, which was initially degenerate, it starts splitting. And with increasing strain, you start seeing that the splitting is becoming more and more. And not only this has a profound influence on the PL as well. So you can see that in region 3, where the PL is uniform, where there was no strain, this is how your PL intensity looks like. But when you go to region 2 here, so you see PL is quenched and the intensity shifts, the peak position shifts to higher energy. And the way in which one can intuitively understand this is because the strain affects the band structure. And when you are having this kind of a uniaxial compressive strain, so basically your K point, the bands are getting more shifted and you have more components from more effect of this indirect combination, indirect transitions. But when you are at tensile strain region, that is here in 1, you see that the peak is much more pronounced here, the intensity is more. And in this region, you see that basically your bands are coming even more closer, thereby you are having more of direct gap transitions. So apart from this, there are also other interesting things one can look at from the spectroscopic signatures. For example, these are bi-layered WSE2 samples that we have been growing. So these are, the inside actually shows the optical images. It looks perfect bi-layered, but once you look at Raman, you see that there are stark contrasts in the intensity of Raman on one side of this plate compared to the other side. So this is something which we have investigated, and we see that it is because of a difference in the stacking between the bottom layer and the top layer. So in this region, you have the 2H stacking, and in this region where the Raman is less, the peak intensity is less, you have the 3R stacking, and this effect is actually seen because of the difference in the resonant and non-resonant Raman scattering. When you basically excite with a resonant excitation, which in our case is a green laser, so your excitation is very close to the band nesting features. So in case of 2H spectrum, it is basically in resonance with the C exciton here, and that is why you see this kind of a increase in the Raman intensity. So I think with this, I will now conclude. So I have been able to tell you how van der Waals epitaxy, a new type of epitaxial growth mechanism, is interesting, and it holds prospects for large area growth of 2D and quasi 2D materials. We have interest in looking at chromium telluride systems, which are interesting materials for looking into skermions, and also how the substrate interactions with the 2D materials, how effective strain and band structure can be identified from the interaction of the substrates. So I would like to acknowledge the facilities, collaborators, and all the funding agencies, and thanks for your attention.
Thanks, Dr. Kochar, for a nice talk. Question.
Hi, nice talk. I missed the earlier part, but we also work CRT chromium telluride system, but CR2T to be precise. I would like your comments on distinguishing, apart from imaging, which only few groups in the world can perhaps, do like those low temperatures, image and look at the fermions. The criticism often that is heard is distinguishing non-trivial spin textures from fermions and calling it topological. Although people say topological Hall effect, that doesn't qualify because you can
Yes,
always
because
write.
any kind
Yeah,
of.
you can have
kind of-
multi-channel anomalous Hall that can give
Yeah.
rise to king, so that's not
Yeah.
a quantification. So can you comment on this, like, do you have experience in, like, when you go to meetings, like what do you hear and how?
So
How do you think
normally,
is a-
people consider Lorentz stem as the ultimate probe for.
But you can't do it at low temperature and,
Yeah.
not every.
It's still one can do at low temperatures. There are specialized group,
I
which
see.
can look at till 77 Kelvin. and that's-
77 is okay, but.
Yeah, beyond that, it's kind of difficult.
But you only see the bubble dance.
Yeah,
Right.
yeah, but I'm hoping people like Kasuri can come up with some techniques where
Right.
we can look into these kind of stuff.
Actually, this is the perfect system to, once we set up the 4 Kelvin system for full wide field, then I think it's the perfect system. Because the plates are also fairly large in size and it's not a very small system as well if you compare the scale. I think this is a perfect kind of.
Yeah.
Well, you and me.
Yeah, and also it's like you have a system where you already have a wide super potential
Right.
and you want to see what happens to these fermions if at all they are affected by the moirates to collaterals. So those are kind of new systems what people have not yet studied. So that's our interest in making and studying these kind of systems.
But are there, like, in your experience, I'm just looking for your comment on, like, distinguishing between non-trivial spin texture to fermions? I mean, other than Lorentz stem, what do you struggle to do usually?
No, we actually, even if you look at transport, so there are three, one is the ordinary Hall effect, then you have you have the anomalous Hall effect. So this is like for a standard ferromagnet, but on top of that, if you are having unusual features like, the topological Hall effect, then maybe we can say that there is some kind of parallel textures, but it has to be correlated with some direct observation. That is what I feel.
So you spoke about stacking image and NCR.
Yes.
So in one case, inversion symmetry is for the high
Yes, yes.
Because it is not broken and it
In clear, it is inversion symmetry is broken, and in fluid, inversion symmetry is maintained. Yes.
So that we have a distinctive signature in the measurement of physical properties.
Yes, for example.
Spin polarization.
Yes, spin polarization, and also people have been talking about ambient ferroelectricity in case of 3R. So
So
yeah.
are you planning to carry out?
Yes, so yes, we do have plans of looking at 2D ferroelectrics with these kind of materials.
The question from students. If not, they are left.
Okay.
Thank you, ma'am, for your nice presentation. So, you have shown that various, you have grown this CRT2 material from top of different substrates. And you have seen that the thickness of the CRT2 decreases if we use the graphene and lead. So, why is this so?
Yes,
What is the parameter that use the thickness?
Yes, so it's basically the van der Waals nature, because in graphene and HBN, you have very small number of dangling bonds when compared to sapphire, and also you have an atomically smooth surface. And because of that, what happens is the add atoms that are getting absorbed on the surface of graphene or HBN, they can easily diffuse and form. And basically, so if you see when you have a material which is growing, the edges of the materials are highly reactive. So whenever the add atoms which are absorbed on the surface, they can diffuse easily and then get attached to the edges, then you have a nice layer by layer group that is happening.
What is the minimum thickness from this
So at least in the case of quadrate 2D, I think we have been able to bring down to 4 nanometers as of now. But it's also dependent upon the temperature, so lower temperature you can also do it.
Fermions are supposed to be fermions. 2 is so affected by 2 pi. Negative. This fermions originally in particles were supposed to be fermions.
Okay.
If you rotate it by 2 pi, they will stay -9. So that can be after here.
Yeah.
No, it's fermion. 2 pi rotation will be.
Funny. I'm not funny.
I see. Okay.
So actually the type of fermions and the chirality, people have been looking at it in Lorentz stem. So depending upon the contrast one sees in Lorentz stem, you can actually think about the chirality. But transport is kind of in very early stage to look at fermions.
If I like comment. So what I know is that you take fermions, whatever texture it is, you map each of those bits on a block sphere. And then how many times does it wrap the block sphere? That can be either +1 or -1. This has been looked at. But right now, okay. Oh, I see.
Can you change the twist angle by this technique by any chance? So we have been looking at twisted by the WSC2, but that is basically we have been taking one WSC2 stacking on the top of the other. But currently in our group lab, we are trying to do twisted by the WSC2. So one way in which you can do is in the first layer that you're doing, if you can introduce some kind of defect or some different adapter or something that can basically change the local growth dynamics and you can induce twisted structures. So we are looking into that. In this case, how much was your MV? The Moiré what pattern you have to? So the Moiré period is actually 1.5 nanometers. So I need to actually look at the angle from that. Yeah.
The sense of speakers on small. We can go into the next speaker. It's my pleasure to hand over this token of appreciation on behalf of Vision Center. With the discussion. Our next speaker is Dr. Chandrima Banerjee. Dr. Banerjee presently is assistant professor at IIT Kanpur. And area of research is experimental condensational physics and several aspects, studying several aspects there. Dr. Banerjee did her PhD from our Center, and then she did postdoc from Trinity College and Technion Israel. Chandrima, you have 25 minutes. Okay.
Okay.
So here the time will be shown. It is total 25 minutes.
Okay.
Around 20 minutes or 5 minutes, you can stop if you want to take some.
Okay, so thank you, Professor Bhumi, for the kind introduction. And thank you, the organizers, Professor Shamim, Professor Tanushree, for inviting me here today. I'm very grateful. And it is always a pleasure to come back to this institute as I did my PhD from here. So anyway, I am Chandrima Banerjee. Hello everyone. And today I will talk about the topic of optospherometry, which basically lies at the interface of optics and magnetism. In particular, I will talk about manipulation or control of magnetic order using very short, energetic optical pulses. So, may I have a pointer, please? Okay, so the words in optospectromics are basically motivated by the drive to push the computation technology from the conventional scalar or electron charge based to a vector, namely speed based one. In the conventional electronics, we have electron charge as the parameter, and the computation is performed by the presence or absence of electron charge, which is controlled by external voltage. So this kind of technology is suffering from heat consumption and limitations to further downscaling. On the other hand, with speed-based technology, we have more parameters, so more freedom. For example, we can use the magnetization direction as a parameter, and we can write the data bits by simply flipping the magnetization direction and use them as 1 and 0. On the other hand, also we can use the magnetic excitations in the form of magnons or spin waves as the carrier waves, and then perform logic operations using them. So when we say that we want to incorporate the speech system into technology, there are a few aspects that we need to consider, such as what is the writing time to write the bits. Also, what is the energy that is required to write this, etc. etc. Basically, we need to cope up with the speed or the rate at which the data bits are flowing in the circuit in the form of current or optical pulses. Therefore, we need to understand how the system behaves or responds at very short time scale. This is where optical pulses comes for help. Using optical pulse excitation, we can study the spin excitations as well as its transient behavior and its correlation with the electrons and the lights. So this gives rise to new physics, as well as it is possible to manipulate the magnetization state using optical pulses only. So let me start with some basics. As we know, in a magnetic system, the magnetic moments are mostly aligned due to exchange interaction, and this alignment of the magnetic moments gives rise to free magnetic charges at the edges. And to reduce that, the magnetization is supposed to be reduced and domains are formed. Apart from this, there are several other energies such as anisotropy energy, Z-man energy, etc. So when a magnetic field is applied to the magnetic system, it experiences a torque by that, and it undergoes a precision about the effective magnetic field, which is given by this Landau-Lifshitz-Gilbert equation. Now the question arises that how does light interact with the spin? In general, light does not interact with the spin system directly. The interaction of light with magnetization can be perceived as an asymmetry in the response of left and right circularly polarized lights. In reflection geometry, this is known as magneto-optical current, where if we reflect a linearly polarized light from a magnetic medium, a rotation in the polarization direction is observed. The same effect in transmission geometry is known as Faraday effect. And in case of absorption, it is known as magnetic circular diffusion, where in presence of magnetization, there will be a difference in the absorption of left and right circularly polarized lights. So this was about how light is affected in presence of magnetic medium. Now, when we have very short optical pulses that has high energy, light can affect the magnetization as well. Overall, we can think about the interaction of light with the magnetic medium in two ways. First is the laser-induced heat. Because the optical pulse has a very high peak energy, it can raise the temperature of the system to a very high value, far above the Curie temperature. On the other hand, the electromagnetic field of the light can couple with the magnetic medium, and that can also affect the magnetic behavior. So in our discussion today, we will focus on to this laser-induced heating effect only. So here I have shown a typical data where the response of the magnetization, the transient behavior of the magnetization is shown as a function of time. So initially, as you can see, the sample is magnetized, and which is shown by this normalized signal on the left side of this time zero. As soon as the optical pulse hits the system, it excites the electrons. The system goes to a highly non-equilibrium state, and the magnetic order is lost, which is shown by the sudden jump in the signal. Afterwards, the electrons, the spins, the lattice state just relaxes back and give away the energy to the substrate and to the environment. So after this by-exponential recovery, the initial magnetization order is gradually established. Now this sudden transient and non-equilibrium heating of the system and the corresponding magnetic disturbance may give rise to several other phenomena, such as the magnetic anisotropy may drop, magnetic precision can be triggered, a temperature-dependent magnetic phase transition may occur, and it is even possible to optically manipulate the spin system. So with this, Let me now move to the next section of my talk, where I will discuss about ultraburst magnetization dynamics in a compensated ferrimagnetic Hertzler compound, manganese ruthenium gallium. So in this case, I used this measurement technique, time resolved magnetooptical pump probe spectroscopy. So in this experiment, I used very short optical pulses, which comes out of the laser at a repetition rate of 1 kilohertz. The pulses have a pulse duration of only 200 femtoseconds, and pulse energy is of the order of 1 millijoule per pulse. Subsequently, these pulses are used in a pump probe manner to excite the magnetization and to probe their dynamics down to sub-picosecond time scale. So, this is the schematic diagram of the setup that I used. As I mentioned, I used here infrared optical pulses, 800 nanometer. After coming out of the laser, I'm not going into the detail of the setup. I will just give an overview of it. So after coming out of the laser, this red beam, 800 nanometer beam, it is very intense. It falls on the sample sitting here, and it excites the magnetization. The subsequent dynamics is then measured by this frequency doubled beam, this blue beam. This is called the probe beam of wavelength 400 nanometer. Now, in our experiment in this time resolved magnetoptical spectroscopy, I used this two-color dual pump probe scheme. 2 points to be noted. First is a delay here is introduced using a delay stage. But when I excited the sample, I did not use a single pump pulse, but rather I used 2 consecutive pump pulses. So another time separation between pump 1 and pump 2 was introduced using this Michelson interferometer-like arrangement. So in the picture we have now 3 pulses. Pump 1 excites, then after some time pump 2 goes, it excites, then probe goes and it measures. Okay. Now before going into the experimental details, let me briefly introduce the sample under study. As I mentioned, I measured here thin films of half metallic compensated ferrimagnet, manganese ruthenium gallium. So this is basically a ferrimagnetic structure where there are 2 kinds of spins, manganese sublattices, and they are antiferromagnetically coupled. As we can see here, 2 manganeses are antiferromagnetically coupled. Therefore, they give rise to a very small net magnetization, which is perpendicular to the film plane. These two manganese sublattices have a very slight difference in their temperature behavior. This gives rise to a temperature where these 2 sublattices exactly cancel each other and the net magnetization is exactly 0. This is called the compensation temperature. Because in our study using optical pulses, we use sudden heating inside the sample, the temperature dependence of the magnetic subcomponents plays an important role in our study. Another interesting fact about this sample is its density of states. Being a magnetic material, it has a spin-dependent density of states, but at the same time, it is a half metal. Because of that, there is a spin gap of about 1 electron volt for one spin direction only. As a result, the electrons from one manganese sublattice primarily contributes to the Fermi. This has a direct impact on our measurement. Because we are using infrared optical pulses, we are primarily probing the electrons near the Fermi level only. Therefore, in our measurement, we are only seeing one manganese sublattice. We cannot measure the other sublattice and neither the net magnetization. This is actually very helpful for us because this is why we can optically image the domains even when the system is completely compensated. So the net magnetization is 0. So with this information in mind, let us now move to my experimental works. So in my experiment, when I used optical pulses and applied them onto the sample, a very interesting phenomenon occurred. It showed that the magnetization toggled to opposite direction each time an optical pulse was fired on it. So it flips to opposite direction with the application of each pulse. So here it goes. So we took the magnetic sample, we fired an optical pulse onto it, and we took the image of the domain of the surrounding area where the laser pulse was shot, and we observed that that a domain with opposite magnetization direction has appeared in the affected area. Now the second optical pulse comes and the magnetization switches back again. So toggle switching of magnetization is happening with each optical pulse. So these are my experimental results. So this basically shows different areas of the sample surface where a number of optical pulses were fired as shown by these numbers. Here the bright and dark contrast represent the up and down direction of the magnetization. And as we can see for both initial magnetization direction, bright and dark, when we fire an optical pulse, the magnetization switches. Then the next pulse comes, it switches back. With the third pulse, it switches again, and so on. So the toggle switches, so a single pulse toggle switching of magnetization is observed in this sample. Interestingly, this toggle switching of magnetization was observed only when the compensation temperature was above room temperature. So this is an interesting result that I wanted to show. For this sample, the compensation temperature is very close to room temperature. So what happens when the compensation is close to room temperature? The net moment is really zero, close to zero. So it is very difficult to saturate the system. So we could not basically saturate this magnetic sample with the available magnetic field in our lab. And we can see the presence of these small speck-like domains in the picture. Now, as we fired the optical pulse, we observed that each small speck-like domain switched. Although the size of the domain was far smaller than the laser spot size. This is very interesting because it shows that this single pulse toggle switching of magnetization is very robust and can even occur in samples which are not affected by stray magnetic fields. So these kind of systems are potentially useful for magnetic data storage systems where small domain can be written as a data bit and which will not be affected by the surrounding magnetic fields. So with this, now I move to the measurement of magnetization dynamics in this sample. So for that, I picked two samples. One has compensation temperature below room temperature and the other has compensation temperature above room temperature. So this sample did not show any optical switching and this sample switched with the application of each optical pulse. If you notice, the orientation of the signal is actually opposite for these two systems because we are optically seeing only one surface, which has opposite orientation below and above compensation temperature. Now, if we look at this data, we will see that initially the system was magnetized. Then as soon as the pulse hits, the magnetization gets disturbed and then it relaxes back to the initial condition in like tens or hundreds of picoseconds depending on the optical pulse fluence. Now as we move to the other sample, after the magnetization is disrupted, instead of going back to the initial state, it now goes to the opposite direction, so it crosses zero. So this shows that the magnetization switched. From this data, we can say more or less the switching time is about 2 picoseconds. So now we know that one of the sublattices after the optical pulse excitation switches in about 2 picoseconds. But what about the other sublattice? We do not have any information on that. And ultimately, what is the switching time for the net magnetization? So to get some answer to these questions, we used this dual pump scheme. In this scheme, we first excited the sample with single pulse So the magnetization switched. Then we excited the system with another pulse. So it switched back. Now, the switching of this second pulse will occur only after the magnetization has already switched by the first pulse. Then the system has to come back to equilibrium and the temperature has to come down below compensation temperature. Then only the second pulse can act on it. Therefore, if we can keep on reducing the time separation between the two pulses, there will be a minimum time below which will not be able to re-switch the system. So that is what we did. In this inset, we can see that with the first pulse, the magnetization switches. With the second pulse, it switches back. Now we keep on reducing the time separation and we measure the dynamics. To get a clearer picture on it, we took the domain images after firing the two pulses. So with single pump pulse, the magnetization switches. With two pulses, it switches back. Now we change the time delay between these two pulses. Initially, up to 80 picoseconds, this re-switching was occurring nicely. But as we go further below, as we reduce the time separation further, we see that below the 69 picoseconds, there is a dark spot still present in the middle of this plot. So this means that the second pulse could not switch this region back. As we understand that because these pulses have a Gaussian shape, when the second pulse approached the sample, the temperature of the central region was so high that the second pulse could not switch it back. As we reduce the time separation between pump 1 and pump 2 further, this unswitched region, area of this unswitched region increases until below 12 picoseconds, where we could not re-switch the system back at all. So now to reduce the effect of this heating, we decrease the pulse energy, and now the system could be re-switched for some more, for even faster rate. So I repeated this experiment for a number of laser pulse energy, and we observed that this, so here basically I have plotted this re-switch fraction, the fraction of the switch region divided by the total region. This re-switch fraction as a function of the time delay between the two pulses. And as we can see, this behavior basically features a sharp drop at around 10 picoseconds, below which it was not possible to re-switch the system back using two optical pulses anymore. So I understand that this is the fundamental limit of the switching process. At this time scale, the net magnetization actually switches and it comes to equilibrium. Therefore, it is ready for the next switching event. So this basically represents the spin lattice relaxation time of this system, and also it gives a switching rate of about 100 gigahertz, which is the fastest all-optical switching event reported so far. So with this, I come to the end of today's discussion, my talk. So in essence, I have shown measurement of ultrafast magnetization dynamics in a compensated field magnetic Weissler compound, manganese ruthenium gallia. It showed an interesting phenomenon by using optical pulses, a single optical pulse, we could switch the magnetization, which is potentially useful for magnetic storage and fast optical communication. The underlying mechanism also shows that new physics are happening inside the system, which open new possibilities for optospintronics research. So with this, I thank you all for this, for your attention.
Thanks, Chunjuma, for very nice job. So.
Thanks for a very nice job.
Thank you.
One nice question. When you shoot a pulse, when you change a magnetization, you shoot it back. Why are there boundaries?
Boundaries.
Yeah, why, I mean, What is the nature of this boundary? Are these certain?
So the nature of this boundary, actually, I also don't, you mean this kind of
Yeah.
thing, right?
Yeah,
This I also don't know clearly. But it is probably some domain wide motion kind of thing, maybe. It still remains after the optical pulse is withdrawn.
The second thing I had is, what about the microscopic spin textures and does that also, is it like what I was saying
Yes.
was, let's say you take a spin glass or some, some system, if you shoot, can you time you all the spin textures or is it like the net?
So, you see, this is basically a special system. Normally, it does not happen that you can switch a material by using optical pulse. So, energetically, it is not possible because the angular momentum has to be conserved, right? But in this case, when we have two antiferromagnetically coupled systems, when it is excited optically, they can exchange spins between themselves, and it is the angular momentum dynamics between them which is actually making them switch. And if you do not disturb the system, they will stay like this forever until you switch it back with another pulse also. So, if we want to do this with other systems, this kinetics has to be there, where the channels for angular momentum transfer has to be there so that this can happen. So far in thin films, only gadolinium, iron, cobalt have shown this. After that, this system showed this kind of phenomenon. And I think it is some kind of spin conservation effect, where the orbital angular momentum is not taking part. But recently, some 2D materials are also showing this phenomena. But if this can be seen, it will be very nice, even in spin glass or any other system.
If you have question.
Yeah, I have actually a related question. I'm also curious about this boundary. It looks very much like the popping effect you see for pneumatic fluid. So if you see that if there's an anisotropy in the system,
Yeah.
always it will migrate to the boundaries and give
Yeah,
you
yes.
So it
Probably
looks
you are
exactly
right.
like that.
Probably you are right.
It's a soft matter phenomena, but it looks very much
Yeah, it may happen because there are anisotropies, strain, all these things are happening, and when this energetic pulse approaches and it is withdrawn, some dynamics is still going on, maybe some domain world dynamics or this soft matter dynamics, maybe we should look into that as well.
Any more question? I have one comment.
Yeah, please.
So in computational industry,
Mhm.
particularly the economics of computational industry governed by this famous Moore's law.
Yes.
So apart from Moore's law, there is another law which is actually physicists are more interested. That is called Ohm's law.
Okay.
So that says that in computational process, due to this dissipation, energy loss is there. And due to this new technology, our aim is to actually reduce this dissipation of energy. And the present belief is that around 20 to 50, Ohm's law will be saturated. Because then we only land up this fundamental cost of computation. So I'm thinking this is opto electronics mechanism, is it dissipating less energy in computation? There is possibility there.
Actually, in my understanding, when so experimentally I saw that it was possible to change the threshold energy required to switch these the systems by changing the compensation temperature. So because everything is happening by exchange of exchange of spin momentum between them. When the spin momentum is low, when you are close to compensation, it was possible to switch the system with very low threshold power. So in spintronics community as well, it is the aim to reach up to that level so that with very small energy and very fast, very short time and small energy we have to reach. And the pulses should not be these femtoseconds because it will be huge system and it will not be very commercializable. So with picosecond pulses and very small energy, if we can make this happen, that will be commercially more favorable.
Thanks, Chandrima, for most stuff.
Thank you very much.
Before moving to the next speaker, my pleasure to take over this. On behalf of Mrs. Our next speaker is Professor Samyukta Roy from RRI. So her research area is ultra cold record atoms, ultra cold quantum gas, in-body physics, Anderson localization. Professor Roy did her PhD from PIFR Mumbai. Then she was IFRAF postdoctoral fellow, CNRS postdoctoral fellow, ERC postdoctoral fellow. Then she joined RRI as Pancharatnam fellow, then PhD scientist, and now she's presently associate professor there. She has got lots of recognition like PhD Women Scientist Fellowship, PhD Award, and more importantly, letter of recognition from ex-Prime Minister Dr. Manmohan Singh for producing the first big condensate in India. Professor Roy.
First of all, I thank the organizers for inviting me to this wonderful conference on women in quantum science and technology. So today I'll be talking about quantum science and technology with ultra-cold Rydberg atoms. But before that, I would like to pay my sincere tribute to Satyendra Nath Bose because I have a strong connection through my work to Satyendra Nath Bose. So as we celebrate the centenary of Bose statistics, we also celebrate the centenary for another very exotic phenomena, which is the Bose-Einstein condensation, which has strong connection with Satyendra Nath Bose. So Satyendra Nath Bose worked out novel statistics for photons and wrote an article, Planck's law and the hypothesis of light quanta, and sent it to Albert Einstein. And Einstein adapted this seminal work by Bose to apply it to other bosonic particles and atoms, and thereafter predicted the phenomena of Bose-Einstein condensation. And so Einstein translated the paper into German and got it published under Bose's name in 1924. And Einstein replied to Bose saying, "It is a beautiful step forward." And thereby Bose statistics was born. Einstein recognized the importance of Bose's seminal paper and generalized his new statistical technique to particles with integer spin and predicted the phenomena of Bose-Einstein condensation. So when the temperature is very low, the bosonic particles will gather together in the lowest quantum state even without any attractive interaction, and this is called the Bose-Einstein condensation. To give you a simplified picture, when at higher temperature, the particles behave like classical particles or billiard balls. And as the temperature is lowered, the de Broglie wavelength, which is inversely proportional to the square root of the temperature, that increases and the quantum nature becomes more and more evident. And at the critical temperature, you see at the critical temperature, this de Broglie wavelengths overlap and you realize Bose-Einstein condensation. And as you lower the temperature further, you have a pure Bose-Einstein condensate, which is like a giant matter wave. So in 2001, the Nobel Prize was awarded to Eric Cornell, Wolfgang Ketterle, and Carl Weiman for achieving Bose-Einstein condensation in dilute gases of alkali atoms. And this was the same time when I had joined my PhD. And I was so much fascinated with this exotic phase of matter and motivated by the strong connection with Satyendra Nath Bose. So I built along with the fellow PhD students Saptarshi Chaudhary, this BC machine under the supervision of C.S. Unnikrishnan. This BC experiment to realize an all-optical Bose-Einstein condensate. So in this jungle of optics, there is this two vacuum chambers where we have realized the Bose-Einstein condensate. And for this, we had realized an innovative design for producing a high flux source of cold atomic beam, which enabled us to have a very large number of atoms in the trap, which led to the successful realization of the Bose-Einstein condensate. And this design was adopted by many other labs around the world because it led to a large number of atoms in the trap for a BC. So this is our Bose-Einstein condensate in a cross dipole trap. So here you can see it's the thermal cloud of atoms before the BC phase transition, and here you see the bimodal structure, which is the famous smoking gun evidence for Bose-Einstein condensate, where you have a dead center characterizing the Bose-Einstein condensate and the thermal background. And as we cool down the atoms to lower temperatures like 140 nanokelvin, which is like 100 million times lower than the room temperature, we get almost a pure Bose-Einstein condensate. So here is the 3D profile for the realization of the Bose-Einstein condensate, and this is the condensate fraction, and you can see clearly the phase transition to Bose-Einstein condensation. And this was the first Bose-Einstein condensate in India, and this was our humble tribute to Satyendranath Bose. So I was happy that in the international media, this news was highlighted as condensation in the country of Satyendranath Bose. So let me switch gears and come to the main focus of this talk, which is quantum science and technology with Rydberg atoms. So I'll give a brief introduction to quantum technologies with Rydberg atoms, and then I'll talk about our recent results on Rydberg atoms, especially a Doppler-enhanced quantum magnetometry. And then I'll talk about observation of Rydberg excitation in cold atoms, and also the effect of interatomic interaction, which is very important, which makes Rydberg atoms very promising for quantum technology. And then I'll give a future perspective on scalable quantum network and quantum sensing with tracer arrays of single Rydberg atoms. So Rydberg atoms are exotic atoms with the outer electron in a very highly excited state. So Rydberg atom was discovered by Johannes Rydberg, and he found an empirical formula linking the various vehicles of the spectral lines in alkali atoms, and this played an important role in the birth of quantum mechanics. So before I go into the Rydberg atoms, the properties and the characterization, so let me talk about what is quantum technology. So it's the acquisition, storage, transmission, and processing of information using quantum sensors, processors, and transmitters. And this has broadly 4 regimes: quantum communication, quantum simulation, quantum computation, and quantum sensing and metrology. And I'll show that Rydberg atoms are useful to explore all these various regimes of quantum technology. So the fact that the outer electron is in a very highly excited state, so this gives Rydberg atoms a lot of exotic properties. For example, it has a large size. So these are giant atoms, and they are ideal for exploring the mesoscopic quantum regime. And also the radiative lifetime, which I was discussing this morning, is it has a long lifetime, which goes as n cube, where n is the principal quantum number to which the outer electron is excited. And it gives a long coherence time to Rydberg atoms for quantum technology applications. And another very interesting property is that it has large polarizability, which goes as n to the power 7. And this makes Rydberg atoms extremely sensitive to small DC or AC electron fields, and hence they are very promising for quantum sensing and metrology. Now, one of the most important characteristics of Rydberg atoms that it has strong interatomic interaction. So the dipole-dipole interaction goes as n to the power 4, and the van der Waals interaction goes as n to the power 11. So what are the consequences? So we can create quantum entanglement via Rydberg blockade and create fast quantum gates for quantum computation. We can do quantum simulation of many-body physics and quantum matter systems, and Rydberg atoms can act as a very deterministic single photon source for quantum communication. So Rydberg blockade was explained in the morning by Raka. But I'll give you an experimentalist point of view. When there are two atoms very far apart, they are not interacting. But when they are coming closer, so if you have one atom which is excited to the Rydberg state, so there is an energy level shift because of the strong interatomic interaction. And if you have a laser beam which is exciting one atom to the Rydberg state, because of this energy level shift, you cannot excite the other and vice versa. So you can see that there is a correlation which is formed between these two atoms, and this leads to entangled state. The fact that in quantum entanglement is at the central stage, it is evident from the fact that the Nobel Prize in 2022 was awarded to Anna Aspey, John Clauser, and Anton Zeilinger for experiments with entangled photons, which has a very important application for quantum information science. So, cold Rydberg atoms are extremely controllable system. You can control any parameter in the system just as you do numerical simulation. So this highly controllable system makes it extremely promising for quantum technology applications. So this is my experimental group at Raman Research Institute. You see there is a majority of women in the experimental group, but it was not deliberate. My senior most PhD student has submitted her thesis, and she'll be going to Germany for her postdoc next week. And we have theory support from Shobhan Datta in RRI and also Rajishnath in ISR Pune. So how do we detect the Rydberg atoms? We use what is called Rydberg electromagnetically induced transparency. So the EIT was described very nicely by Professor Rupa Manjari Ghosh. So I just give a brief description of our system where we get the Rydberg EIT. So we use a ladder kind of system where we excite first the atom to the first excited state, and from there we use another, which is called a coupling laser, to excite to highly excited Rydberg state. And here we get, because of the destructive quantum interference of these two transition probabilities, we get a Rydberg EIT signal. So this is the Rydberg EIT signal which we get in our experiment. And when we started our experiment, we didn't have the transition frequencies for exciting to very highly excited Rydberg state. And as you saw, that higher we excite into the Rydberg state, more exotic are the properties because it goes as principal quantum number. Now, to get those frequencies, we thought, let's measure them ourselves. So when I was doing my postdoc in Paris, so I happened to hear a talk by Theodor Hansch, who said in his talk that when he was doing his postdoc with Arthur Shallow in Stanford, the one piece of advice he gave him is that always measure frequencies. And this he took very seriously, and it led to his invention of the optical frequency comb, for which he received the Nobel Prize in 2005. So keeping this very useful piece of advice in the back of my mind, we measured this transition frequency of very highly excited Rydberg state all the way from n equal to 45 to n equal to 125. And from there, we also got very accurate measurements of quantum defects, which characterizes the deviation of the Rydberg atoms from the hydrogen-like behavior. So next I come to an interesting result which we have got last year, which is Doppler enhanced quantum magnetometry with Rydberg atoms. So generally when you want to do a Rydberg excitation, we have this probe and the coupling laser in a counter-propagating configuration to compensate for the Doppler shift as much as possible. So we adopted a non-traditional way of this excitation. That's what we have the probe and the coupling laser in a co-propagating configuration. And to understand this better, we have applied a magnetic field using a solenoid. And to our surprise, we found that the Zeeman splitting, or the response to the magnetic field in this unconventional co-propagating configuration, was an order of magnitude larger as compared to the conventional configuration of counter-propagating configuration of the probe and the coupling beam. So in collaboration with Shobhan Datta, who is the in-house theorist in RRI, we did the theoretical modeling and we could get an excellent agreement with our experimental results. So this will be published in New Journal of Physics. So the focus of a lab is cold Rydberg atoms. So this is our experimental setup where we realize the cold atomic cloud, which is around 20 microkelvin temperature. And we have two complementary detection systems. One is the EMCCD camera, and we have avalanche photodiode for detecting a few photons from this Rydberg atoms. So this is the experimental configuration for exciting cold Rydberg atoms, cold atoms to the Rydberg state. And here, 2 years back, we got the first signal from cold Rydberg atoms. And so this was the first and presently the only cold Rydberg atom experiment in India. And this is an important milestone because it opens up avenues for exploring the various regimes of quantum technology with this very versatile system of cold Rydberg atoms. So we went ahead and also measured the very strong interatomic interaction between the Rydberg atoms as we go to higher principal quantum number. So here, as you can see that at n equal to 35, we have this signal from the cold Rydberg atoms. And as we go to higher n, which is 55, we see a broadening. And from here, we could estimate the interatomic interaction. And we have also got signatures of Rydberg blockade effect. So this is the experimental strategy we have adopted to have the Rydberg excitation in a very stable kind of configuration. So we are locking this to Rydberg excitation laser to a high finesse reference cavity so that we have a very narrow laser line bit so that we can have a large coherence time in the system so that the system is stable over a long period of time. So the next step in our experiment is to have individual atom trapped in an optical tweezer. So for that, we have treated optical tweezer using a dipole trap beam at 850 nanometer. And the idea is to have the focus spot of this optical tweezer very small, around 1 micron. So this will ensure that there is collisional blockade effect. And if there are more than one atom in this optical tweezer, both of them will have inelastic collision and both of them will go out of the trap. So this ensures that either there is 0 or 1 atom in the trap. And we have high numerical aperture lenses placed inside the vacuum chamber to enable the single atom trapping in the optical tweezer. The importance of addressing single quantum systems is evident from the fact that the Nobel Prize in Physics 2012 was awarded jointly to Serge Haroche and David Weitland for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. So we have progressed significantly in this direction, and we have characterized this optical tweezer outside the vacuum chamber because we cannot measure inside the vacuum chamber. So we have replicated the whole system outside, and we have measured submicron focal spot, which enables us to have a single atom trapping in the optical tweezer. And we have also realized an array of this optical tweezer for having quantum technology applications like quantum computing with array of individual Rydberg atoms. So now I come to the future directions with the Rydberg atoms. So the future directions are quantum information and quantum sensing with cold Rydberg atoms. So while we were making this array of optical tweezer, is that it is very useful for making a scalable quantum network with this individual Rydberg atomic qubits. So the idea is to have individual atoms trapped in these optical tweezers, and then we excite the atom to the Rydberg state and create quantum entanglement between them using the Rydberg blockade effect, and thereby make an array of scalable quantum network of this Rydberg atomic qubits towards quantum computation. Also, another very interesting regime to explore via Rydberg atoms because of its large size is the mesoscopic regime. So we all know that in the microscopic regime, what is followed is the single particle physics. And in the macroscopic regime, it's the many body physics is dominating. So what happens in the mesoscopic regime? So what are the microscopic properties which give rise to this macroscopic properties in a macroscopic system? So to explore and Rydberg atoms being giant atoms, they're just in this Goldilocks regime where we can explore this intriguing mesoscopic regime. So the idea is to have atom by atom assembly and develop a 1D or a 2D array of this individual Rydberg atoms and explore the scalability in this system and make a scalable large network of this Rydberg atom qubits to make a Rydberg atom quantum computer. So we can also explore quantum many-body physics with Rydberg atoms as was described in today's talk in the morning by Raka. So we can not only make 1D or 2D arrays of this individual Rydberg atoms, but we can also make a triangular or a square array of this Rydberg atoms. And then we can do the quantum simulation of many-body physics and look at anti-ferromagnetic ordering with Rydberg atoms. And we can also, with this kind of system, which is highly controllable, we can address many open problems in quantum magnetism. Another new direction I'd like to explore in the system, which has not been explored anywhere else, is to combine this long-range interaction in Rydberg atoms with disordered potentials. And here there are a lot of possibilities, and probably we can explore new quantum phases in such kind of system. As I had described before, that Rydberg atoms, because of this high degree of polarizability, are extremely sensitive to small DC or AC electric field and hence very promising for quantum sensing and metrology. So the idea is to have a single Rydberg atom in an optical tweezer and use it as a very sensitive, very accurate quantum sensor for microwave, terahertz, or RF electromagnetic radiation. So we can choose any energy level structure for the Rydberg atoms and use it as a very sensitive quantum sensor for microwave or terahertz radiation. With this, since it's highly sensitive and highly controllable system, we can hope to beat the standard quantum limit via quantum tricks such as three-state and probably reach the Heisenberg limit, which is the holy grail of quantum measurement. So with this, I have described how cold Rydberg atoms are a versatile system where we can, with which we can explore the various regimes of quantum technology like quantum computation, quantum sensing and metrology, quantum simulation. We can do emulation of complex solid state systems, and we can do also ultra-fast quantum dynamics. And we can also use it as futuristic dipole antenna for observational astronomy. So this is a very versatile and highly controllable system. So I come to the end of my talk. So I have described our recent results on Rydberg atoms and Doppler enhanced quantum magnetometry. And then I have described the Rydberg excitation in cold atoms. And then I have given a future perspective on how we can do quantum information and quantum sensing with cold Rydberg atoms. Thanks for your kind attention.
Thanks, Professor Roy, for nice question.
You mentioned quantum magnetism with ultra-cold Rydberg atoms. Yeah. So one interesting phenomenon is the study of quantum phase conditions.
Yes, yes.
And the typically external magnetic field relativity parameter.
Exactly.
And the critical value of the field for BOSEStat plane or indicator of magnetism.
Yes.
Exactly the same for BOSEStat and conductive field.
Yes.
So what is the possibility of the quantum phase conditions to be kind of?
So as I was saying that Rydberg atoms in an array of optical tweezer is a very highly controllable system. We can control any of this parameter in this kind of system. For example, we can control the interaction. We can just have it at any principal quantum number which will control the interaction, or we can take it far away or put it closer. So this gives us also control in the interaction. So this is a long range interaction, and this helps us simulate, do a quantum simulation of the physics of the many body system in this any kind of condensed matter system. For example, we can explore even spin glasses, which you were mentioning in your talk. We can have, frustration and random coupling in such a system because it's highly controllable, and we can, also simulate spin glasses in such a system. This has not been explored, and it's like there are many open problems which can be explored because it's a very versatile system. So it can be easily explored in such a system.
It's a very nice job. Just one comment. I think somewhere in the video you mentioned that you want to continue this work by adding some strong disorder and something.
Yeah.
I think you made a statement that that's not being explored much. But as far as I know, in context of many body visualization, there has been a lot of experimental work, at least by simulating quasi-periodic outboundary kind of potential, and also some with random disorder control.
Yes. So what I was saying that the combination of Rydberg atoms with disorder has not been explored much. So I myself have worked in Florence on Anderson localization of 3D in 3D disorder potential, where we had very accurately measured the mobility edge, which is the transition from a disordered from the diffusive phase to the disordered phase in a 3D disordered system. So, and also there are many body physics also explored in the system by combining interaction and disorder. By combining the long range interaction of Rydberg atoms with disordered potential is still, an open system where people have not explored much. There are theoretical papers which has come from Subir Sachdev in Harvard University, like they have predicted Kibble-Zurek mechanism which can be explored in such a system. But as experiment, this has not been explored much, where Rydberg atoms are, put in a disordered potential. So there are a lot of possibilities and open questions which can be addressed in such a system.
Any more questions? I have one question. So you have mentioned that this Rydberg atoms in optical tweezer can be intact, as it means. So any experiments so far has been reported? Any experiments so far?
Yes.
So finally, how they, in some correlation, let's say it's created, how they measure the length angle?
Yeah, so in Rydberg atom system, what is done is that if you have okay, so I can just tell you that if you have the atoms to the excited to the Rydberg state, now you have two hyperfine ground state. Now you have the excitation from the upper hyperfine ground state. Now the Rydberg state is mapped to the lower hyperfine ground state. So if you measure the atoms in the lower hyperfine ground state, that means it was excited to the Rydberg state. So now you can measure how many atoms were excited to the Rydberg state and how many are not. Because now you can measure atoms in both the hyperfine ground state. So now when you do this measurement very fast, you can measure the fidelity of this entanglement, which has been realized in such kind of system.
So, but these Rydberg atoms, they are not spatially too much separate. No?
That is completely controllable. So that's why we are putting it in optical tweezer rather than in optical lattice. In optical lattice, we don't have much control. So we can just, vary the angle between the lattice, but all of them will have same distance. But in optical tweezer, each of the tweezer are independently controllable. We can just make them closer, farther, so we can control anything in the system.
So if that is possible, I think then this is could be one of the candidates to test this Bell test here.
Yes,
Because
of
that
course.
requires the spatial separation.
Exactly. Yeah, yes.
So we have another question, because answer speakers once more. Before going to the lunch break,
So good afternoon, everyone. Welcome back to the International Conference on Women in Quantum Science and Technologies. Just 2 more sessions left for this conference. And to chair this session, I would like to request my colleague, Dr. Pradeep Pachfule, to come and introduce the speaker.
Good afternoon all. Welcome back after the post-lunch session. It's my pleasure to welcome our own student, Dr. Swastika Chatterjee. She did a PhD from SN Bose National Center of Basic Sciences. She was also Inspire faculty at IIT Kharagpur, I guess. And currently she is working in IISER Kolkata, and her research is mainly concentrated in the areas such as study of electronic magnetic and structural and elastic properties of minerals under high pressure. Also, she works on the strongly correlated materials. So, Swastika. Stage yours, 20 minutes plus 5 minutes for the question and answer.
So when does the time start? The moment I end. Okay.
It's not so clear.
Okay, so before I touch, start করে দিয়েছি? Okay, so before I start, I would like to extend my apologies because what I'll present right now does not exactly fit into the domain of quantum technologies. Nonetheless, it is a very important application of quantum sciences wherein we are able to study the interior of the earth. So we all know that it is very difficult to know what is happening deep inside the earth, right? You cannot dig into the earth and see what is happening inside. But there are definitely indirect studies. The best among them is seismology. But seismology on its own cannot tell us anything. It just gives some elastic properties of the interior of the earth. So if you want to decipher what seismology is telling you, then you have to have mineral physics data. So mineral physics data can come from experiments, high pressure, high temperature experiments. So performing such experiments, that is where you have to go to pressures of around 360 gigapascals, temperatures of around 6,000 degrees centigrade is non-trivial in the laboratory. So the other alternate method, which has been extremely successful in deciphering what is there inside the earth, is the first principles density functional theory, which we have used in this study. So before I start with the talk, I'll quickly read through the title. It reads Influence of Water on the Post-Spinel Transition at the 660-kilometer phase boundary of the Earth. And that's the first principle study. So I presume it's difficult for you to understand what it means. But as I go through the talk, I'll try to walk through each and every term I've written here and try to help you in understanding what I'm trying to say. Okay, so beyond the hustle and bustle of everyday life, if you look below your feet, you would see that there is continuous motion, right? And this is what is known as plate tectonics. And this specific plate tectonics is something which is responsible for formation of the continents and also reforming it again and again. But before we dive into plate tectonics, let us first see what is there inside the earth, which is important to understand plate tectonics. So if you dive deep into the earth, you know earth is made out of different layers. It could be a compositional kind of layering or a mechanical kind of layering. I can use this. Okay, so if I look into the compositional layers, you basically have a very thin, rigid crust followed by a mantle, and there is a core. So what it means is that the core, for example, is compositionally different from the mantle and the crust, and so on. The mantle is further divided into upper mantle, transition zone, and lower mantle. This is something will come next. So this is the mantle. At 410 kilometers below my feet, upper mantle goes over to the transition zone, and at around 660, no, this is the depth that I had mentioned in my title. The transition zone ends and the lower mantle starts, and below this portion, you basically have the core of the earth. So if you look into the mineralogy, the most dominant mineral phase in the upper mantle is olivine, which transforms into its high pressure polymorph wurtzlite, which is a spinel at around 410. Now somewhere around here, wurtzlite transforms into another spinel structure, which is ringwoodite. And at 660 kilometers, the depth of our interest, ringwoodite breaks down into a perovskite structure, which is known as bridgemanite, periclase, and so on. But right. So now that we understand the compositional layering, let us look into the mechanical layering, which is more important to understand if you really want to know how the earth is behaving in the interior. So the top of the earth, there is this rigid lithosphere, which is made out of the crust plus some portion of the upper mantle. Then comes the asthenosphere. So you know that as we go deeper into the earth, the temperature and pressure keeps increasing. So with rising temperature, the rocks in this asthenosphere, they are basically not exactly fluid, but they can flow. So as a result, this lithosphere can actually glide over the asthenosphere. Deeper inside, you have the mesosphere where the pressure is really very high and hence rocks here are very rigid. Then you have the outer core, which is metallic but liquid because of the very high temperature. And finally, at the center sits the solid inner core, which is solid because, once again, of the extreme high pressure. Okay, now that we understand the composition of the earth, or what is there inside the earth, let us get back to plate tectonics. So it is in the early 1900s, a scientist named Alfred Wegener, he was basically looking into the coastlines of the continents, and he felt that these continents can fit into each other like a jigsaw puzzle. So he was so interested in that he proposed that once upon a time the continents were all together. He also named them. This is a supercontinent. He named it to be Pangaea, and this is basically the Greek for all the earth. Now, as with all branches of science, any abstract idea is very difficult to accept. So this is what happened in the case of Wegener's theory. But fast forward today, now we all accept that this is basically the foundation for plate tectonics theory of the earth. So what exactly is plate tectonics? So the outer mechanical layer, that is the lithosphere, is divided into large continent-sized plates, and these continent-sized plates they're continuously moving, right? But the movement is pretty slow, about 1 to 2 inches per year. And this is precisely the reason that about 100 years ago, scientists could not really appreciate what Wegener was trying to say. But what changed in between? So there are several evidences which came in favor of plate tectonics. The first one was disappearance of dikes. So around 1950s and 1960s, scientists, it was mostly US Navy who were trying to basically map the submarines. So they found that there are cracks in the oceanic crust, and there were magma oozing out of these cracks, and those magma were forming new rocks and new crust. Okay, so that basically tells that the crust is continually reforming itself, or new crust is being formed time and again. No sooner scientists started plotting the locus of earth plates around the earth, and they found that this locus matches quite well with the plate boundaries that were proposed by Wegener. And finally, the final piece of evidence, which made things very evident, was the fossils that were found in Africa were of non-native tropical species. So Africa doesn't have a tropical climate. So it basically says that sometime in the past, millions of years ago, Africa was somewhere else. So remember Pangaea, right? So this is what finally sealed the fate of plate tectonics. And hence, what we have today is the modern plate tectonic theory, which is a very new theory developed some around 45 years ago. So how it all works, according to plate tectonics theory, the massive plates are all moving in different directions, and how they interact with one another can have a huge impact on the earth. Now, where these plates meet, they are called boundaries. So there are 3 different kinds of boundaries. The convergent boundary, where plates hit against each other. Then you have transform boundaries, where plates glide against each other. And you also have divergent boundaries, where plates move away from each other. So what are the things that can happen at a convergent boundary? So what happens is that the first thing that can happen is that the lighter or a less denser plate can actually dive below the more denser plate, giving rise to what is known as subduction zone. So we need to remember this because this is what forms the basis of our talk. So this is where basically crust is being destroyed or engulfed into the earth, right? Now, as the plate moves down, it creates pressure, and with it, you have a lot of temperature. So together that basically melts the rock here, and you basically have volcanoes. So this is the ring of fire around the Pacific, which consists of volcanoes because of such convergent boundaries. Then the other thing that can happen is that when these two plates come closer to each other, they can fold up, forming mountains. So this is what formed Himalayas. So even today, the Indian plate is continuously hitting against the Tibetan plate, and the Himalayas are still growing at a rate of 1 inch per year. And the final thing at convergent boundaries, what you can expect is earthquakes, right? When they're pressing against each other, though the pressing is very slow, it can generate a huge amount of pressure, and that pressure can get released in the form of earthquakes. Okay, so now that we are done, next is transform boundaries. This is where plates would glide against each other, and once again, you can have earthquakes at such transform boundaries. This is the San Andreas Fault in California. This is where plates are gliding against each other, and along this fault, you get a lot of earthquake. And finally, divergent boundaries. So where plates are moving away from each other. So the first thing that can happen is that you can have a rift forming. So this is something which is seen in Africa. So there's a rift forming in Africa, and very soon in geological terms, that is in thousands of years, this part of Africa is expected to break away and move very closer to India. Okay, and then if this plate is under the ocean, then the crust is narrow and you can have magma oozing out and forming new land. So we saw that at subduction zones, crust was being destroyed. Here, new crust is being formed. So it's a continuous process that is taking place, a similar picture. So yeah, this is another example of divergent boundary along the mid-Atlantic ridges. Okay, so now that we understand that plates move, the next question is, why do plates move at all? Okay, and the reason is we have a very hot core sitting at the center, and it is trying to cool itself, right? So it's basically because of large scale convections that the plates are moving. So geological processes are ultimately consequences of Earth's cooling with time. Therefore, the origin of oceanic plates at the ridges, the movement of these plates, and their final consumption into the Earth's deep interior is basically a result of large-scale convections. Okay, so now we concentrate on the subduction zone, right, where plates are going deep inside the Earth. So these subducting plates can go, for example, up to the 660-kilometer boundary or maybe deeper, right? We don't know to what depths do these subduction plates go inside the Earth. So this is something we would like to answer, and this is basically my research problem here. So to what depth do these subduction plates go? Why is it important? So that basically would give me an idea about the nature of the convection going inside the Earth. Whether it is a layered kind of convection, where the upper mantle is convecting on its own, or the lower mantle is convecting on its own, or it's a whole mantle convection that is taking place, right? So once again, I get back to the slide I showed you earlier. So we are basically looking into this 410-kilometer and 660-kilometers boundary. So apart from these dominant mineral phases, olivine, wurtzlite, ringwoodite, bridgemanite, there are also other mineral phases present, but it is because of phase transitions in these minerals, we all understand that these transitions, these boundaries are created. Okay, so to understand whether the slab will go deeper into the mantle or will stay afloat or stagnate, we would basically now invoke thermodynamics, things that we have studied during our college. So what we'll try to do is that we will try to figure out the Clapeyron slope of the phase boundary. I hope everybody remembers Clapeyron slope, right? So if the Clapeyron slope is positive, what does it mean? It means that as temperature increases, the pressure at which the transition will take place will also increase, right? Alternately, the temperature decreases, the pressure at which the transition to the other high pressure phase would take place would also decrease. Similarly, if I have a negative Clapeyron slope, it's just the opposite. So if temperature increases, then the pressure at which the transition would take place would decrease and vice versa. So what if we have a positive Clapeyron slope? So when we're talking about subducting slabs, they are basically cold slabs, which is surrounded by the hot mantle, right? So if it is a cold slab and the Clapeyron slope for the phase transition is positive, then I would expect that the transition inside the slab would happen earlier than the rest of the mantle. So if the transition happens earlier, then the slab becomes much denser and there is a high probability that the slab will penetrate through the boundary, right? On the other hand, if the Clapeyron slope is negative, then the transition inside the cold slab will happen at a greater pressure than the surrounding mantle, and as a result, the slab that was coming down is expected to stagnate. Why? Because it is of lower density than the surrounding mantle. So this is another cartoon of the same thing. So for the olivine to Wadsley transition, which is the 410 kilometer transition, it is now well established that the Clapeyron slope is positive. So mind it, the zero is here. So although it looks like a negative slope, it is actually a positive slope. So if this is positive, then you expect the slab to basically penetrate through the 410 kilometers boundary. This is well established. So any slab would penetrate the 410 kilometer. But what about this transition, the 660 kilometer transition? Here, it has been found that the slope is negative, right? So you expect that the slabs would stagnate at this point. But seismic studies suggest that slabs have been found in the lower mantle. So there is some way that these slabs are actually going down deeper into the mantle. Okay, so these are our results. I'm not going into the details of the results. So what we did is that it is known that minerals in the transition zone, they are all hydrated. So we have basically extensively studied the Wadsleyite and ringwoodite phases, how water gets in there and stuffs like that. So the next question that we basically asked is that it is known that if I consider the mineral to be anhydrous, the slab will stagnate. What if the mineral is hydrated, right? So this is the question we asked. And our calculation, so if the mineral is hydrated, so hydrous ringwoodite, if it breaks down into hydrous bridgemanite and periclase, we did the calculation and found once again the slope is negative, indicating that the slabs are stagnating. Okay, but later experiments showed that bridgemanite can take very little, insignificant amount of water. So this reaction itself is not probably correct. So the water must be going somewhere else, right? So there are very recent papers that show that the silicon dioxide quartz that we know, its high pressure polymorph stishovite is stable under lower mantle pressures, and that this phase can take a lot of water. So, and there are several evidences in favor of that. I'm not going into it. So what we did is that we looked into this reaction, hydrous ringwoodite breaking down into anhydrous bridgemanite. There's a magnesium oxide and a hydrous stishovite phase, right? So when we looked into the Clapeyron slope for this reaction, we got a positive number, plus 1.57 megapascal per Kelvin. So that basically tells me that there is a probability that if the slab breaks down in this manner, the slab can actually penetrate into the lower mantle. So these are the details of our calculations. I'm not going into it. So in summary, we have basically studied the influence of water on the breakdown of ringwoodite at high pressure and temperature using first principle study. So the transition of dry ringwoodite to bridgemanite had a negative Clapeyron slope, and that suggested that slabs wouldn't penetrate the 660 kilometer boundary. But with the new reaction mechanism that we have brought in, we see that there is a gentle positive Clapeyron slope that basically gives us an indication that there is a possibility that the slab might penetrate into the lower mantle, and that in turn indicates that the mantle convection is probably not a layered mantle convection, rather it's a whole mantle convection taking place. So acknowledgements. This is my mom, this is how she looked when I was doing my PhD. Okay. I cannot acknowledge her enough in general, but I'm acknowledging it scientifically as per this talk. So we have extensively worked on the hydrous phases together. Gaurav Shukla was also involved in it. This is the PhD student, Rabindranath, who has done the calculations. This is Professor Jivamitra Ganguly, a veteran geologist who assists us in understanding our results. And finally, a thank you from my biological and non-biological kids. And before I end, since this is a women in science kind of conference, Raka wanted me to highlight this lady, Zainab Ghulabi Mahmoodabad. So she is an Iranian. When we talk about challenges for us women, it's insignificant as compared to what she had to go through. So this is a lady who is almost my age. She came back to science after 12 years. So she completed school in Iran. Then she had her own personal life. Finally, after 12 years, she came to India. She did her bachelor's from Mysore University. So at that time, she didn't even know how to speak English. So she had brought her brother. She used to speak in Persian. He's the one who used to translate to English. She did her bachelor's, master's, and then finally she came to me for her PhD. And I was more than happy to have her in my group. And also, I would like to mention that she is a hardcore geologist and she has worked really very hard to understand physics. DFT ma'am knows she has published data. So this is a woman I would like to highlight before I end my talk. Thank you so much.
I wonder what's the especially the last slide you were showing about right? It's based on
Oh, so this is something which has come up new in Kalyani.
Okay, so wonderful to listen all of these things, like how all of that and most to Panji and all. So questions.
What's the name of this lady? Once again, it's Iranian.
Zainab, Zainab.
It's a PhD with you?
Yes.
So, so I have a couple of questions actually. So these minerals that you're, talking about the different phases, I guess you have done the calculations, but in reality, when experimentalists do their studies on these materials, these are synthetic materials or?
No. The moment you call something a mineral, it means it has been found somewhere. For example, when I'm calling bridgemanite, I could call it the bridgemanite because in 2014 it was found in a meteorite. Before that, physicists had done the experiment. They saw ringwoodite breaks down into, they would call it a perovskite phase. So perovskite phase got a name bridgemanite only after it was discovered in a meteorite. So the very definition of mineral has it that it has to be found naturally.
So that brings me to the next question. So, when you say experiment, what kind of experiments are you talking about? Are people studying like magnetic phases, or what kind of like bulk magnetism in these minerals, or
So I haven't talked about magnetism as such. So when I'm talking about experiments, I mean, so generally all scientists use what is known as DAC, diamond anvil cells, to produce extreme high pressure and temperature, right? And once they do it, they have to do like at the presence of the pressure and temperature, they have to basically investigate the crystal structure. So that is what I told is challenging. You have both high pressure and temperature, and then to be able to identify the crystal structure. So what we are mostly interested in is the elastic properties, because what we know about the Earth comes from seismology. Seismology is nothing but waves and gives us information about elasticity, right? So what experimentalists would do is determine the structure and then simulate different things out of it. That would happen by hand. Thank you. Thanks.
So you talked about that magma and then forming the land. So I wanted to know what makes this land stable. Because as we know that Japan, I think, also happened the same thing. Japan came out like that. But now there's some problems with the water, with the rising sea water.
I just want to know what makes this land stable. Okay, so stability basically comes from density, right? If it was denser than what is there inside, it would sink. So whenever the magma oozes out, it cools down, forms a very dense phase. That makes it stable, right? Japan, you're talking about water rising.
Yeah, I think
That is due to global warming.
I think there's some news that Japan might also
Sink. That may be because the sea level is rising.
Indonesia also that.
It's because the sea level is rising, because ice is melting somewhere else. Yeah. Okay, I should admit before I end. No, I am not a trained geologist. So I have very limited knowledge, but I'm learning and I'm actually enjoying learning.
I have a small question. And any of these minerals be extracted from the subduction zone or the volcanoes near the subduction zones?
If you are lucky enough, if there is some rock that is popping out from there, shooting up, and you get it. For example, I said that the transition zone is hydrated. We did not have any direct evidence. Still, there was a diamond which popped out from that region, had hydrous ringwoodite in it, and that was an indirect evidence that suggested that the transition zone is at least locally hydrated, if not globally.
One small question, because what determines this, whether this tectonic plates will too short to like what you are trying to mention about the convergent or
Yeah, that must be proper physics. Like what started it off, I wouldn't even try to answer that because I haven't studied to that depth. So I will try to figure it out and get back to you, like whether it comes together or far away.
Last question. Sound velocity, is it different in this kind of hydrated or non-hydrated?
Yes, sir. So we have extensively studied. We have two very good papers in that area. One is there. So that is basically what we do, sir, is that we calculate the elastic properties and then calculate sound velocities and then match with seismic wave velocities. Okay, so our job is firstly to look into the stability and then also to match with seismic wave. The moment it matches well, we can say that this is a probable phase, let's say.
If there are no more questions, let's thanks once again to Dr. Chatterjee.
So I would now like to request the session chair to kindly hand over the memento to Dr. Swastika Chatterjee.
Okay, let's move to the next one. So now our neighbors from ISS Kolkata who did a PhD from Sainika Bhowal. So she did a PhD at ISS Kolkata and she did a postdoc at University of Missouri in USA. Then she was also a postdoc in ETH Zurich. And currently she is working in IIT Bombay Physics Department. And her research interest is to understand, predict, and design material exhibiting unique electronic, magnetic, and magnetic, electronic, and transportive properties, and how these properties impact on the quantum prevail. Yeah, stage yours. 20 minutes plus 5 minutes.
Thank you for the nice introduction. First of all, I would like to thank the organizers for this invitation and to give this opportunity to present some of our recent research works here. It is always good to be back to Kolkata and yeah, I mean, during my PhD, I also worked with consultants with Gupta, so I visited SMUs for some time, and so it is always nice to be back here. In today's talk, I will be talking about orbitronics. So I'm a condensed matter theorist. I'm curious to search for new physical effects in real materials. And here in this talk, we will discuss about
orbitronics, which is actually an emerging field of research, and it is analogous to spintronics. It provides a platform for exploring this quantum science and technology. In today's talk, I will particularly focus on the background of orbitronics, some of the recent research progress, including my own contribution, and finally, I will point out a few open directions in the field that I am also interested in working with. So, advancement in semiconductor physics led to the discovery of electronics, which created a revolution in technology. Following this evolutionary path of electronics, spintronics emerged as a breakthrough in technology where it overcomes the limitations of traditional electronic devices. The key idea of spintronics is to use the spin moment of an electron rather than its charge to carry information. And this basically leads to enhanced storage capability, faster processing speed, reduced power consumption, and so on. The spin moment of an electron, the up and down spin moments, can be used also as qubits in spin-based quantum computers. What makes these qubits apart is basically its ability to exist not only in 0 and 1 states, but also a superposition of these few states that we also heard in many previous talks today. And there has been a very recent interest in developing and building these quantum computers. And yesterday we had a discussion about this national quantum mission also. Orbitronics is actually a new frontier which overcomes the strong spin-orbit coupling requirement of spintronic devices. In today's talk, I will focus on this orbitronics and in particular the orbital Hall effect. So Hall effect in general can involve three fundamental degrees of freedom of the electron: charge, spin, and orbital mode. And the consequent effects are known as Hall effect, spin Hall effect, and orbital Hall. In the same way as Hall effect forms an inseparable part of electronic devices, and spin transport in spin Hall effect is an important part of spintronics, orbital Hall effect is also at the center of orbitronic synthesis. And the two main breakthrough, namely this Bailey phase and the concept of Bailey phase and modern theory of orbital magnetization, these are the two things that form the backbone of orbital Hall physics. So I will start with a brief recap of Bailey phase and Bailey curvature. Consider a generalized eigenvalue problem, simply h phi m equal to E phi m, where the Hamiltonian h has parametric dependence on lambda that varies slowly with time. Now, what we want to know is what happens to the wave function as time evolves. For an atomic process, for a long time, it was believed that this wave function picks up a phase that can be gauged away, so it's meaningless. However, Bailey in 1984 showed that while this is true for any open path in the parameter space, if this path is closed, the wave function picks up a phase. That phase is actually gauge invariant and hence is a measurable quantity. This phase is called Bailey phase, and actually such a concept of geometric phase was already introduced by Pancharatham in the context of optics, so this is also often referred to as Pancharatham Bailey. Now, interestingly, the Brillouin zone of a solid forms an excellent platform where we could investigate these Bailey phase effects. The reason is, if we look at the Schrodinger's equation for the periodic part of the block function, we realize that this Hamiltonian has an explicit dependence on parameter k. So consequently, we can define Bailey phase as the Brillouin zone as a contour integral of a vector quantity called Bailey connection, or equivalently as a surface integral of another vector quantity called Bailey curvature, which is basically part of Bailey connection. Now, there is an interesting analogy between Bailey connection and magnetic vector potential, and Bailey curvature with magnetic, basically similar to magnetic vector potential. Bailey connection has a gauge dependence, whereas similar to magnetic field, Bailey curvature does not have such gauge dependence, and in fact, Bailey curvature is a quantity that appears in various unusual Hall conductivities. So in 1879, Edwin Hall basically discovered this Hall effect, but soon after this discovery, Hall himself realized that there are some unusual behavior in the measured Hall conductivity for ferromagnetic metallic systems. So this behavior was not understood. Hall reported this behavior in 1881 and named this effect as anomalous Hall. It actually took more than a century to understand what is happening. So in 1995, Chang and Yu pointed out that because of the Bailey curvature, this semi-classical equation of motion for the electrons are modified. And what happens is that because of this additional term, even in the absence of magnetic field, the electrons experiences a force, a velocity basically, which is perpendicular to the applied electric field. And this velocity is called anomalous velocity, and this explains the behavior that was observed in Newton. Consequently, we can write down this anomalous Hall conductivity as a Williamson integral of the Bailey curvature. Now, if we look at the symmetries of the Bailey curvature, then it seems that Bailey curvature can exist in the momentum space if either of these two symmetries is broken. However, for anomalous Hall conductivity to exist, it is not sufficient to have non-zero Bailey curvature, but this integral has to be non-zero. And this requires the time reversal symmetry to be broken as well. And one of the example materials where this is the case is the ferromagnetic materials. In a ferromagnetic system, basically you have unequal numbers of up and down polarized electrons, and therefore there is an imbalance in the number of electrons that are accumulated at the edges of the sample, and this leads to a transverse flow of charge current, which is also spin polarized. And so this effect is called anomalous Hall effect. Now consider the case when there is no net magnetization, so in all magnetics. In this case, we have equal numbers of up and down spin polarized electrons. So there is no net flow of charge in the system, but still we have an imbalance in the spin moment, and this leads to transverse flow of spin moment, and this effect is known as spin Hall effect. Orbital Hall effect is a counterpart of the spin Hall effect, where we have a transverse flow of orbital moment rather than the spin. The concept of orbital Hall effect was actually introduced already in 2005. This is around the time when spin Hall effect was also came into notice. And not only in this particular work, but in several other works, it was highlighted that orbital Hall conductivity has a large magnitude. The main breakthrough in this field really came from this particular paper by Coe et al., where for the first time they pointed out the origin of the orbital movements that actually contributes to this Hall effect. Because there's conventional belief that orbital moments are quenched in a solid, so how the orbital moment actually appears in the first place to have this orbital Hall. And what they said is that if we apply an electric field in the Hall effect, then in the non-equilibrium electron distribution, we have an overlap of different orbitals, and this leads to basically hybridized complex orbitals which carry a net orbital moment. And then these orbital moments flow in opposite direction to give rise to this orbital Hall conductivity. So the main source of this orbital Hall effect is this k-space orbital moments. Now, two characteristics of this orbital Hall effect that actually gain a lot of attention to this field, and these are basically the fact that this orbital Hall effect can exist even without spin orbital effect. This means that even light element materials can be good candidate materials to observe this orbital Hall effect. And the second thing is that since which actually follows from this first point, that it does not require spin orbital coupling, which means that its magnitude is also not limited by the energy scale of spin orbital coupling strength. And indeed, the magnitude of orbital Hall conductivity often found to be much larger in computation compared to spin. However, all these works are actually limited to centrosymmetric systems. However, we already now have the modern theory of orbital magnetization. And this modern theory of orbital magnetization says that even in a non-magnetic system, if the inversion symmetry is broken, then the orbital moment can be present intrinsically at equilibrium, not only in non-equilibrium, but at equilibrium. So this is the formulation that we have from modern theory of orbital magnetization. It has a very similar form to wave curvature, and accordingly, the symmetries of orbital magnetic moment is also very similar to wave curvature. So under time reversal, it switches sign, whereas under inversion, it does not. Therefore, even in a non-magnetic system where the time reversal symmetry is preserved, if the inversion symmetry is broken, then in the case space we could have non-zero orbital moment. Note that since the time reversal symmetry is preserved, therefore, if we sum over the entire Brillouin zone, then orbital moment at plus k will cancel out with that at minus k. So the net orbital magnetization in the system is 0, which is expected because of the presence of time reversal symmetry. Now, with this idea, we particularly looked into this family of transition metal dichalcogenide systems. So these materials have already been introduced in several other talks in the morning session. And this is actually a work that I did during my postdoc at University of Missouri with Shashi. And here is the crystal structure of this transition metal dichalcogenides. So in the top view, you can see that the transition metal atoms form a triangular lattice. In the side view, the chalcogen atoms are out of plane, and so they bring inversion symmetry. Now, if we consider these neighboring transition metal atoms, and in particular these orbitals, dxy and dx square minus y square orbitals, then you see that from Slater-Foster hopping parameters, the hopping is not allowed between these orbitals. However, in real materials, of course, we have these chalcogen atoms that break inversion symmetry and accordingly induce a hopping between neighboring orbitals. So it leads to an effective GD hopping in the system. And this effective GD hopping is very crucial because this leads to formation of complex orbitals of a form like this, which carries a net orbital moment. And indeed, in our computational work, we see that these value points, K and K prime points, these are high symmetry points in the Brillouin zone, they have oppositely directed orbital modes. So whenever these K and K prime points appear in the Brillouin zone, the orbital moments are equal and opposite. So this leads to a value orbital node. Now remember that this material has time reversal symmetry, and in fact this K and K prime points are connected by time reversal symmetry, so that's why the orbital moments have this opposite direction. So it is consistent with the symmetry as well. Now, the orbital moment has the same symmetry as the wave curvature. So these valley electrons, they also have opposite wave curvature. This means that when we apply an electric field, these valley electrons gain opposite anomalous velocity. This further implies that if we apply an electric field, these oppositely directed orbital movements will flow in opposite directions, giving rise to an orbital interactivity in the system. And this entire process here is actually occurred in the system even without spin orbit coupling. In fact, in the presence of spin orbit coupling, which is of course present in the real material, what happens is that these orbital movements in the K space couples to the spin degrees of freedom, and in this way, the value orbital locking leads to spin value splitting. So spin value splitting is actually very well known in these materials and has been studied for a long time. And here we see that it originates from this value orbital locking. So orbital moment is more fundamental in that sense in these systems, and with spin orbit coupling, they couple to this spin degrees of freedom, leading to this spin value split. And consequently, orbital Hall effect leads to spin Hall effect in the presence of spin orbit interaction. Now, from this understanding, we can
expect that this non-centrosymmetric system, since they have this additional source of intrinsic orbital moment in the reciprocal space, therefore they will have larger orbital conductivity. To actually demonstrate that, we consider this model system. So this is a work with 30. So this is a BCC lattice with two atoms, one sitting at the corner and another one sitting at the center of the unit cell. So the structure has inversion symmetry, but we can move this central atom artificially, and then it breaks inversion symmetry. And we studied the orbital polyconductivity as a function of the displacement of this central atom. What we see is that as the displacement increases, the orbital polyconductivity magnitude also increases. And we further decompose the contribution, the orbital polyconductivity into two contributions coming from centrosymmetric part and the non-centrosymmetric part. And what we see is that the centrosymmetric contribution actually remains more or less unaffected by this, whereas the non-centrosymmetric part quickly picks up, and it is this quantity that actually changes the total orbital conductivity. So this shows that in a non-centrosymmetric system, the orbital polyconductivity has a larger magnitude compared to its centrosymmetric. Now, a common question that comes into mind for this 2D broken inversion symmetric systems is that what is its connection to Valley Hall effect? Because Valley Hall effect has been studied for a long time for this monodiazole transition metal dipole device and also for gap graphic systems. So in what way, Giovanni, we showed that this Valley Hall effect actually can be better understood as an instance of orbital Hall effect. By reformulating the Valley Hall conductivity in terms of this orbital Hall conductivity, we are able to remove some of the ambiguities regarding the definition of Valley Hall conductivities. So for example, we can remove these abstract Valley indices by more physical quantity like orbital magnetic moment. We also no longer have any arbitrary cutoff in the value restricted integral, because now in the orbital Hall conductivity, it is a full Brillouin zone integral, which is well defined. It also provides us the platform to avoid these purely conventional Valley current, because the sign of the Valley current actually depends on how one defines it, whereas in the orbital current, it is very well defined. In fact, if we define the Valley Hall effect in terms of these orbital moments, actually it helps us to also understand the main measurement, the power rotation microscopy measurements that have been done long time back to detect the Valley Hall effect. In these measurements, actually what is measured is the accumulated orbital moments. So it is better to describe it in terms of orbital Hall conductivity rather than Valley. And in fact, we can generalize this effect to bilayer systems also, and this is what we did in collaboration with IBM. Now, so far I was talking about orbital Hall effect, but it is also possible to think about other orbitrons effect, and one of the effect is basically kinetic magnetoelectric effect. So this is an effect where an electric current induces an orbital magnetization. And interestingly, there's a class of materials called polar metals where the electric polarization coexists with metallicity, which is very unusual, but in nature such materials do exist. For such materials, actually, there is a texture of orbital magnetic moment in the base space, and this texture can be controlled by switching the direction of the electric polarization. This offers the possibility that the corresponding this kinetic magnetoelectric effect can also be switched by controlling this electric polarization. And we can also describe this orbital texture in the multipolar description, where we could identify real space or carried charge multiples, which is nothing but a quantitative measure of asymmetries in the charge density in the real space. So this multiple formalism offers us the possibility to predict what would be the pattern of the orbital texture in the reciprocal space. And such an effect actually can also exist even in transition metal dihalogenide systems, but here it needs this additional strain engineering. So to summarize, we have seen that so far there has been some progress in theoretical understanding of the mechanism of orbital Hall effect, both in inversion symmetric and non-centrosymmetric systems. In a very recent time, actually, there are some experiments that came up which also have shown the presence of orbital Hall current in real materials. So the kind of setup that has been used is shown here. So it is an interface between a non-magnetic and a ferromagnetic system. The non-magnetic part is the source of orbital Hall effect. So when we apply an electric field, this an orbital current is injected, which exerts a torque on this magnetization, and by measuring the deflection of the magnetization vector, one can detect the injected orbital current. So now that there are some experiments which have proven the existence of this orbital Hall effect, it might be interesting to see how we could tune this effect in real systems, and that will help us designing also orbitronic devices. So in future, it would be interesting to know what are the factors that control this orbital Hall effect, and if we can control it using an external stimulus. The relation of orbital Hall conductivity with band topology has also not been explored so far. In fact, so far all the theoretical works have been done only for non-topological systems. But since it is correlated to Bailey curvature and orbital movements that significantly depend on the band topology, so it is more likely that topology will affect the orbital Hall conductivity magnitude. Finally, I mean, there is also other orbital ribbon effects can be present. For example, now people have started looking at orbital rush bar effect, which is actually an orbital counterpart of spin rush bar effect. And once again, the idea is similar. So basically, orbital rush bar effect occurs as a more fundamental effect, and then with coupling with the space, it translates into spin rush. So hopefully all these works will motivate also future experiments in this direction. So with this, I'd like to thank you for this.
Yeah, nice to see that all the drawings and all the logic is getting proven by experience there. So, Stephen, open for the questions.
I'm a little curious. Of course, you have this orbital Hall effect when there is no button needed. It's primarily geared by breaking of inversions. Of course, you know that when you have the inversion symmetry broken, and you have also sufficient spinoid coupling, what you can have is anomalous, non-linear anomalous. Right. Not in a linear order, as you very rightly said, but in the non-linear order in the remain. But then if one, as you very rightly said also, that in a real material, there will be some amount of spinoid. It's not zero. So then you have basically two different possible effects. One is this orbital Hall effect because of this inversion symmetry breaking, and maybe there is an orbital moment couples with that spin, and that's a secondary effect. But on the other hand, you will also have a non-linear anomalous Hall. So I don't know how to disentangle these two things. It will of course depend also on the strength of the spin-orbit coupling. I mean, which one is the primary and which one is the secondary. But is there any kind of study on this? So
Actually, I mean, this is a very good question. In the field, what was challenged, especially from the experimental point of view, is to disentangle this orbital and spin contribution. So in these experiments, actually, what I didn't really describe it here, but what happens is that the orbital current that is injected, that exerts a torque on this magnetization, but it actually first couples with the spin orbit coupling of the ferromagnetic material. Whereas if this is a spin current, then it will exert a torque directly on the magnetization, so it does not depend on the spin orbit coupling strength of the ferromagnetic material. So for this kind of setup, what experimentally they did is that they changed this ferromagnetic layer, different for ferromagnetic layer with different spin orbit coupling. They found that actually this strength is different. So that is an indication that something of orbital origin is coming at the interface rather than the spin. Now coming back to your question of this nonlinear Hall effect, actually I did not discuss again here, but this here in this paper we discussed two universal responses. One is this kinetic magnetoelectric effect, and the second effect is this nonlinear Hall effect. And this nonlinear Hall effect actually can be understood from the fact that as a first order effect, there is a generation of orbital magnetization, and then this orbital magnetization as a second order effect to the electric field gives rise to this nonlinear Hall effect. And in experiments, basically one can do measurements like they can probe light with frequency omega, and then the nonlinear Hall effect will have a frequency 2 omega, and so that's how they can distinguish.
Okay, thanks.
If there are no more questions, next time, speaker Hexagin.
So I request the session chair to kindly hand over the memento to Dr. Bhawal. There. No. I would like to thank Dr. Pradeep Panchpule to chair the session. And I request our director, Professor Tanushree Shah Dasgupta, to please hand over the memento to the session chair.
Please carry.
So we are going to now take a short break, but please come back after the tea break. We have two more talks, and the final talk is actually a talk from the publisher's side, from IOP Publishing, where they will talk about some unique perspectives of women in science. So I will urge you that please have tea and then come back. So we should meet, yeah, that's what we should meet here at 3:45. 15 minutes, okay? 3:45. Hi, Tushna, can you hear us? Hello?
Hi, yes, I can hear you. Can you hear me?
Yeah, we can hear you very well. So
Oh, excellent.
share your slides, or I can open the slides from here. What do you prefer?
Actually, let me see if I can. Sorry, I'm a bit more used to Teams than Zoom because we use Teams over here, but let me see. I'm sure I can quite easily share
Yes.
my if you give me a second. Oh yeah. Okay, so
Yes, we can see your.
yeah,
Yeah,
you
we
should
can see your
you
slide.
probably see my folder for a minute,
Yeah,
and
we can
then
see your screen, so that's
excellent.
now if you open the presentation, that should work.
Yeah. So I think that should yeah. Are you seeing the presentation now?
No, we see only your screen actually, the folder. We don't see the
Ah,
presentation.
I think it's just I've launched it. I've launched it. Maybe it's just a couple of seconds lag if you can't. Do you see the presentation now?
No, not yet.
Oh.
Can you share once again? Just please share the entire screen maybe.
Yeah, that is what I have.
Hold on. So. Uh, Okay, give me a second. I'll stop it, and I'll do it again.
It's coming.
Yes, ma'am, we can see now. Yeah, and does it look like the presentation now,
Yes,
instead
yes.
of just the, yep,
Yes.
and yeah, the slides, yeah.
Slides are changing. Okay, fine.
They're changing? Excellent,
Yes.
Working
excellent.
fine.
So I think that's fine, then it should be fine, and you can hear me clearly and all of that,
hear
right?
you, but you don't have to leave because there's a talk you can attend.
Yes. Okay,
Because
excellent.
you
So I
never know
think,
if you
No, I know.
connect
Yeah.
back, what kind of problems will crop up? you have
That's
no
true.
idea.
So what I'll do is I'll switch off my audio and video for the next talk,
you
and
have
but
to
I'll
turn
stay
off-
online.
Yeah, that's great.
She has
Yeah.
to turn off the sharing.
But you have to
Yes.
stop the sharing.
Yeah, of course. I'll stop that now. But
Yeah.
yeah, I think it should work fine.
That is fine.
Okay. Excellent then. I'll come back. I'll watch the next talk. That'll be interesting. And then yeah, I'll stay online, but I'll mute myself and switch off the video for now. Yeah.
Okay, thank you very much.
All right. And just in case anything goes wrong, you have a copy of my slides. So in case
then
that
you just
doesn't
go to
work,
the
you can pull
slides
them
thing.
up, and I'll just say next slide, and you guys can share them.
That's
Yeah.
no problem at all. We'll manage.
Perfect. Thank
Okay.
you so much. Thank you. All right. See you in a bit.
See you. So, welcome back everyone to the last session of this conference, International Conference on Women in Quantum Science and Technologies. In this session, we will have two talks. The first talk is by Dr. Parijat De, who is an assistant professor of this center, S.N. Bose National Center for Basic Sciences. She completed her PhD from SINP, Kolkata, Then she did a postdoc at ISC Bangalore, followed by a postdoc at Uppsala University. After that, she was an assistant professor at research at Durham University in UK. Her research interests are understanding strongly correlated systems using conformal field theory, conformal bootstrap, holography, and quantum gravity. And today she's going to talk about proving conformal field theory with defect. So Parijat, please.
So I would like to thank the organizers for giving me the opportunity to present my work here. So I am going to talk about how to prove conformal field theory with defect. I will explain what I mean by all these terms as we go along. So I am a theoretical physicist by training, and since it's a conference on women in quantum science and technologies, we are celebrating women scientists in quantum physics. I thought I should begin by mentioning Amy Noether. So as physicists, we are always interested in finding symmetries which make our lives simpler. So here is Amy Noether, who has made pioneering contributions to physics and mathematics. So she has given us Noether's theorem, which is associated with symmetry and certain kinds of conservation law associated with that symmetry. Okay, so now I will talk about my research. So my research revolves around various aspects of theoretical high energy physics with specific interest in the area of quantum physics, and the focus is on quantum field theory. And I am particularly interested in a subclass of quantum field theory which describes scaling invariant theory, which is known as conformal field theory. So I will talk about this in details. And a large part of my talk is also, a large part of my research is also dedicated to understand quantum gravity, specifically using the techniques of conformal field theory, how the questions in quantum gravity can be addressed, or questions to understand black hole physics. So let me begin by the framework of quantum field theory. So there are many aspects of quantum field theory, and I'm going to talk about only those aspects that is directly related to my research. And here I'm going to show the works of the two gentlemen. So here we have Richard Feynman. In the framework of quantum field theory, Feynman taught us how to compute correlation functions using Feynman diagrams. And these are the diagrams that can give us some numbers that we can actually measure in lab. So this is, although the framework is purely theoretical, you can actually get some numbers and those can be verified. And here is on the other side, we have the Kent Nielsen, who has developed the theory of renormalization group. And these two frameworks are the, I would say, the most important part that of my research. So I'm going to explain how I use this to understand conformal field theory in a bit. So the idea of renormalization group flow. So I have taken this picture from one of my favorite books, so Quantum Field Theory in a Nutshell by Anthony Z. So here we have here's a picture of a theoretical physicist in a lab coat, And as theoretical physicists, most of our time we spend to integrals, and obviously there are some divergences associated with the Feynman diagrams that we get, and we have to spend time to regulate and renormalize those integrals. So here is what he is doing. So he has a chopper in his hand and he is cutting off the infinities. And you can see from the face that he is very much annoyed. Now, there is a way to deal with these divergences that Wilson taught us, which is the idea of renormalization. So the idea is that every physically consistent theory should come with a length scale, beyond which we are ignorant about the physics that is going on. And renormalization is a framework that leads us to calculate physically measurable quantities that are free from all these divergences. So that's why I have put this caption, cutting off our ignorance. So sometimes ignorance is good. Okay, so what do we want to study? So I am interested in understanding various aspects of conformal field theory. What is the that we want to study using this framework? So conformal field theory arises in different branches of physics. It arises in statistical physics, condensed matter physics, and also in gravitational physics. So particularly, it describes the second order phase transition at the critical point. And as we know that at the critical point, a system, the correlation length of a system diverges and the system becomes scaling rate. So that's where conformality plays a role. And this conformal field theory can be used to understand the critical universality. For example, the Ising model is one of the many applications of this conformal field theory. Now, using this conformal field theory, we can also address quantum gravity. So there is a correspondence which is known as ADS-CFT duality. So it means the anti-de Sitter and conformal field theory duality. So this duality means that there is a connection between quantum gravity theory, which lives in anti-de Sitter space-time, and a conformal field theory. So here is a picture. So this is a cylinder, and we can think of this as a solid cylinder, and this is like an anti-de Sitter space-time. And according to this duality, the boundary of this cylinder is described by a conformal field theory. So this duality allows us to compute quantities in quantum gravity theory using conformal field theory. So this is kind of an equivalence between a conformal field theory and quantum gravity. Okay, so now why do we want to study this theory? So the first thing is, in quantum physics, we oftenly encounter strongly correlated systems. So the interaction is very large. So the standard tools of whatever is quantum field theory cannot be applied. So for example, at the critical point, a large number of degrees of freedom are very strongly correlated. So all the known whatever is tools fail. Now, in spite of this difficulty, there is some advantage that is there at this special critical points. So the symmetry at this critical point is enhanced from the usual Lorentz symmetry to a conformal symmetry. So in the Lorentz symmetry, we have the usual Lorentz transformation, and in addition to that, we have scaling symmetry that takes us to conformal symmetry. So the question is, what role does this extra symmetry play? Now, one can understand this from a purely symmetry-based approach, which is known as a conformal bootstrap approach. And I have worked on this symmetry-based approach over the last few years, and here are some references. And this approach is completely based on symmetries and consistency conditions. So it doesn't assume the existence of a Lagrangian or any kind of microscopic shape. So that is where the universality plays a role. And these consistency conditions play an important role to understand the critical universality. For example, all the critical exponents in a particular, in some universality class can be studied using this symmetry based approach. And this approach is free from Feynman diagram or renormalization or regularization techniques. I have also worked on understanding this conformal field theory from a Lagrangian perspective. And specifically today, for today's talk, I'm going to talk about how to understand these systems with defects. I will define what I mean by defects in a bit. And this is mostly based on this paper with Kaushik Ghosh, who is a postdoc at ENS. Okay, so what do we mean by defects? So defects are impurities in physical systems. So here I have to orient ourselves. Let's talk about these two cases. So on the left, we have a spin three-dimensional lattice system, and at each lattice site, we can think that there is a spin degree of freedom. And this lattice is bounded by two boundaries. So this gray colored is at the boundaries. So the lattice is bounded, and the interaction between the spins when they are on the boundary or in the body, that is different. So this is one can think of it, this is like a Ising model with the boundary. On the right, I have a two-dimensional picture of a square lattice, and the black dots are lattice degrees of freedom. And here there is an impurity which is marked as red. So this degree of freedom is different from the rest of the degrees of freedom. And there is a interplay between these different degrees of freedom, and the idea is to understand this system as a whole. So, yeah, as I mentioned in this system, the lattice with the boundaries and interfaces, we can actually study the finite size effects of the system. So, for example, one can also have two different systems with a boundary or interface, and the idea is to study what is happening close to the boundary. Now, these defects can be of different types, depending on the shape and orientation of the defect. So, for example, can be point defects where there is only a defect at a particular point, can be a line defect, where we have a defect along the line, or surface defect, and so on. So, the question that arises is, how do we describe the dynamics of this defect? So, I will now talk about conformal field theory with defects. So, as a theoretical physicist, we always try to understand the system by first writing down a Lagrangian. So, the first step would be to identify the degrees of freedom of the system. So, here I have used the field phi, which is a scalar field phi, to denote the degrees of freedom of the system. And then we identify all possible symmetries that we expect the system to possess. Now, conformal symmetry in these space-time dimensions include these transformations, which is invariant under translation, rotation. There is a scale invariance symmetry, and there is also an inversion symmetry, popularly known as special conformal transformation. So, as you can see from the symmetry structure, the first two are the usual symmetry that is there in the Lorentz symmetry group. And in addition to this, we have these extra symmetries at the critical point. And this theory is invariant under this symmetry group. So this is SO T plus 1, 1. So this is just a notation to denote this group theoretic structure. And once we identify these symmetries, we can write down the dynamics of the theory using this action. So this is a Lagrangian, which is a function of the degrees of freedom and its derivatives. Now we introduce some defects and break the conformal symmetry. So the definition of defect conformal symmetry is that part of the conformal symmetry is broken. So here is a picture. So we have a d-dimensional space-time, and we introduce a p-dimensional defect in this space. So this is the planar defect. So we just space a p-dimensional plane in the entire space-time. And once we place this plane, we can divide the space into
direction. So we have degrees of freedom lying on the plane, or you can have degrees of freedom which is normal to the plane. Now this defect breaks some of the symmetries, but it also preserves some of the symmetries. So for example, the p-dimensional defect preserves the p-dimensional quaternary symmetry on the plane. The rotations in the transverse t minus p directions, and the scaling symmetry is always preserved because the scaling doesn't affect the position of the defect. So with this, we end up getting this residual symmetry structure. So we started with this symmetry group SOP plus 1,1, and after this p-dimensional defect is introduced, we have this SOP plus 1,1 times SOT minus p. And for today's talk, we will be talking about line defects. So which means basically we have a plane and we put a line to break translational symmetry perpendicular to this plane. So here is how we identify the coordinates. So we have the coordinates that live in the entire space-time. So this, I have singled out one coordinate tau just to identify the defect. So this is a picture. So this is a three-dimensional picture with one-dimensional defect. So translational symmetry is broken perpendicular to this direction because here we have placed something. And for simplicity, the location of the line defect can be assumed to be at x equals to 0, where all the other coordinates are 0. Now with this, we can write down a modified Lagrangian, which consists of a bulk Lagrangian plus a defect Lagrangian. So this is a bulk Lagrangian which contains the entire symmetry, conformal symmetry. And here we have this defect Lagrangian, and note that there is a delta function over here whose arguments are denoted by x defect. So it means that this is non-vanishing only when we have the defect. So these are the deformations localized on the defect. Now, once we have this kind of Lagrangian formulation, we can try to understand the renormalization group flow in the context of a defect conformal field theory. So in the left, I have drawn the usual RG flow present in a CFT. So a conformal field theory can be thought of as an RG flow from a CFT in the ultraviolet to another CFT in the infrared. And similar things happens when we have a defect. So we can think of this, the picture on the right, this is a renormalization group flow in a defect CFT. So we can have a defect CFT in the ultraviolet, which flows to a defect in the infrared. And it turns out that when we have this kind of defect, the renormalization group flow is triggered by some kind of relevant defect operators. So this leads to a defect fixed point. So these defect models have been studied earlier by Alias research there in 2014, and then recently in 2021 by these authors. So once we have this defect set up, we can try to understand how to compute the correlation functions at this defect fixed point. And let's talk about the model that we are interested in. We are interested in conformal field theory with n scalar fields with a global symmetry. So we have scalar fields phi I, where I runs from 1 to n. And this is the Lagrangian. So here we have a kinetic term, del phi squared. And here we have a generic quartic interaction. So we have 4 fundamental fields phi I with some coupling lambda, which depends on all these indices, I, J, K, and L. So this can be a generic quartic interaction. Now, this theory can be studied using dimensional regularizations. So what Wilson taught us is that it is sometimes useful to think of a quantum field theory in fractional dimensions. So instead of studying this theory in 4 dimensions, we actually cannot study this at the critical point directly because this lambda is large at the critical point. So strong coupling forbids us to do perturbative quantum computations. So we can do this in 4 minus epsilon dimension, treat epsilon to be a very small perturbative parameter, and compute whatever we want to using perturbative expansion in this parameter itself.
And this is known as the Wilson-Fisher fixed point, which was developed by Wilson, Fisher and Co. in the 1970s. So just to mention that this model also describes the Ising model for a conformal field theory for a particular value of this coupling for a 5-4 interaction, and for when we have only one scalar field, so there is no global symmetry. So this reduces to the Ising. Now, what we do is we insert a relevant defect line operator. So the idea is that we have to break some symmetry. So first we break the global symmetry. So out of n scalar fields, we choose a particular scalar field phi 1. So it can be any of these phi's. So we single out one particular field phi 1 and we add this interaction term, which is localized on the defect. So this phi 1 is localized in the defect where x is equal to 0. So this is the defect term, and here this is the defect perturbation. H is a defect couple. So with this model, we can try to compute the correlation functions. And here in this model, we can study these correlation functions perturbatively in the bulk coupling lambda, where lambda is small, perturbatively order by order each lambda. But this defect coupling H can be exact. So there is no need to assume that H is small. Okay, so these are this is a bit technical, but these are the Feynman diagrams associated with these defect CFTs. So these are the diagrams up to the quadratic order in the bulk cut. So here what we have computed is actually the 1-point function of this operator phi 1, and this red square is a defect coupling which is localized on the defect. Sorry, this red square is a bulk coupling and these black dots are the defect coupling. So depending on how many couplings we have, it will decide the order of the defect or bulk. So as I have already mentioned, this is exactly the defect coupling. So we keep all the diagrams up to an arbitrary order of defect insertions. And finally, we can evaluate all these Feynman diagrams and we end up getting a defect fixed point associated to a bulk fixed point. And these are some of the schematic diagrams that we have. So we can actually compute the 2-point functions. So these are the 2 points in the bulk, and this is the free theory part. This is the interacting part with this interaction vertex over here. These are the 3-point functions, and here we have the 4-point functions. Okay, so I would just like to mention one thing. So we can study the entire thing without using this Lagrangian, using the bootstrap approach that I mentioned in the beginning, using symmetries and consistency conditions, and this matches with the Feynman diagram computation. So this is kind of a consistency check that it works. Okay, so now let me summarize. So what I have shown is that we have a conformal field theory that describes the fixed points of renormalization group flow, and we break this the sum of the symmetries of the theory by introducing some defects. And we have shown that there is a renormalization group flow that arises because of the relevant perturbation added to the system, and this can be computed exactly in the defect coupling. And using this renormalization group approach, together with the Feynman diagrams, we can actually compute the correlation of the defect operators. So I think I should stop here. Thanks.
Thank you very much, Parisa. So time for questions. Yes.
Is your technique very specific to dimensions?
No, this is not linked to dimensions. It's valid in any dimensions, but we have studied this in 4 dimensions.
It was 4 dimensions.
Yeah.
Yeah, really the free space dimension.
Yeah, 3. It's like 4 minus epsilon, and we have we put epsilon equals 1, so it's like 3 dimensions in paradoxes.
So is it possible to have some experimental validation of your
yes
symmetry ratings you were saying? So what will be the consequences of those?
So the thing is that like the particular model that we studied, the phase transition that is associated to to some peroxide, or some phase transition associated from tetragonal to trigonal phase transition, and without this defect, the critical exponents of this theory can be studied, which has already been done. Now the idea is that if there are some impurities in these peroxides, what will be, how will that affect the critical phenomenon? So that those kind of experiments can be done. Yes.
So it seems, so isn't it your surface defect is more common than the line defect? Because you consider the line defect.
Yes, yeah, yeah.
So isn't it the surface defect?
Using this Simon diagram approach, surface defects, it's not yet explored, so there are only like very few papers. Line defect is the easiest one, but of course we are like moving to.
Yeah, that's why I
surface
thought it was the one.
Yeah.
See, I mean, without in the context of iron world, suppose there is a absence of a steam. Would be someone be defective?
Absence of a steam?
Like, for example, you have steam present everywhere. At one place there is no steam.
Yes.
Would that be like a defective?
I think so, yeah, yeah.
It's
So the
okay.
thing is that there's some kind of symmetry is broken, so that needs to be, that is related to the defects.
It's not very simple.
Any further questions? Okay, Monica. Here, sorry.
The four field interaction we have taken, why, any particular reason for that?
So this four field interaction is fine to the fourth theory. This describes the Ising model when we have only one scalar field. And the model that we are interested in, that is related to a peroxide phase transition from a tetragonal to trigonal. So that is the model that describes this phase transition is that is described by this quartic interaction. Yes.
Then another equation for dimension we have written d plus 1 is equal to 4 minus xi.
Yes.
So then d is the dimension. Dimension
D is the
is
dimension.
extended.
Yes.
So then epsilon is what?
Yeah, so the thing is that, so this was developed by Wilson. So the idea is that since this is a strongly coupled system, we cannot study this perturbativity in any dimensions. So the idea is we can treat this dimension as a perturbative parameter. We study this in 4 minus epsilon dimensions and treat epsilon to be very small.
Very small means in a arbitrary real.
Much less than 1,
I
yes.
see.
And then we compute all the,
So it's a mathematical technique.
yes,
Because now this dimension, physical dimension is actually
yes,
meaning.
yes.
But it's a mathematical technique, finally we.
Finally, using this, actually what we showed is all the eigencritical exponents can be computed using this dimensional variable. So this is the technique used in one.
So is it then the physical dimension is D?
So here it's d plus 1. I have written it in this way. So
Yeah.
the total dimension is d plus 1.
Right.
So the perturbative parameter is in 4. Yeah, so this is 4 minus epsilon. So the total dimension is 4 minus epsilon. And if we want to get back the three-dimensional Ising model or whatever results, then we put epsilon equals 1 finally.
So, what the gravitational dual of the bulk of a defect field?
Yes.
Does there a gravitational dual exist?
There are some results, but not for this particular theory. So the idea is that this is a CFT with a boundary. The gravitational dual exists for CFTs with a boundary, but not yet with this specific kind of. There are some works by Tadashi and collaborators that they have done.
I was just thinking that whether the results that you have got,
Yes.
they have been reproduced from some
No.
gravitational dual.
No. The gravity dual is not yet known for this.
The question that I said that here we compute the 2-point functions and the 4-point functions, 3-point functions, whatever.
Yes.
By using a Lagrangian.
Yes.
And there you have a defect part in the Lagrangian
Yes.
density. You also mentioned that you can reproduce all those results by using some form of bootstrap.
Yes.
But in bootstrap, the thing where you don't require any Lagrangian.
Right.
So it is model independent.
Right.
You just require the symmetries.
Right.
But my question is then, how do you know about the structure constants? Because here you are reproducing everything from Feynman diagram computation, you are getting the result, you know the result fully.
Yes.
But there is a part in the other approach where you don't know the structure constants of the three unless you do the Lagrange intensity.
No, the bootstrap constant, if you impose all the symmetries, then the structure constants can also be fixed.
So they can be fixed.
Yes, yeah. So all these results from the Feynman diagram computations, we have verified it also from the bootstrap.
The last question, is this in Euclidean or Lorentzian?
Euclidean.
Euclidean.
Yes.
Okay, last question.
So Parita, your epsilon equal to zero limit for, that would be the 5-4 theory, mean field theory, right?
Yes.
So that way, which is exact because 40.
Yes.
So can I think of this epsilon as some way of accommodating the fluctuations because you are reducing the dimension, so
Yes.
epsilon takes into account that.
Right, right, yeah. So epsilon equals zero limit is the main field,
Yeah.
so it's exactly solved.
Yes.
So that trick is valid only when we go to interactive theory.
Yes. So basically, this epsilon is taking care of the fluctuations.
Exactly, yeah.
Okay, then let's thank Parijat once again for the talk. And it is my pleasure to present to the youth. Oh, mine. What do you need? So this brings us to the last talk of this conference, and it is my pleasure to introduce Ms. Tushna Kamishariat. So she has been associated with IOP Publishing for the last 10 years. Currently, she is features editor at the Physics World, and today she is going to talk about Leading Lights, Unique Perspectives of Women in Quantum Science. So Tushna, if you could kindly share your presentation.
Yes, hi. Good afternoon. Just give me 1 second. I hope you guys can see the PowerPoint now.
Yes, absolutely.
Perfect. Great. Hi, it's a real pleasure to talk to all of you today. So yes, I'm Tushna Commissariat. I'm the features editor of Physics World. And today I hope to tell you a little bit about what we do at Physics World, a bit about my background, and then talk about some amazing women in quantum science that I've had the pleasure to speak to over the past couple of years, and hopefully find out more about yourselves too. IP Publishing is the Institute of Physics Publishing. We're wholly owned by the Institute of Physics, which is a charity based in the UK. And our main aim is to spread the joy of physics and get more people into physics. So IP Publishing is based in Bristol. We publish many journals that hopefully you guys are aware of, magazines, conference proceedings, and mainly our main magazine now is Physics World, the magazine and the website, and we have authors from all over the world. A bit about my background. So I did my BSc in physics in St. Xavier's College in Mumbai. That was a long time ago in 2009. And then I wasn't quite sure if a career in academia was quite made out for me. So at the same time, when I was applying for MSCs in physics, I also applied for an MA in science journalism. I'd always enjoyed science writing and communication, so I thought that might also be a good route for me. And I was quite lucky that I was accepted to the first cohort of science journalism MA, the first cohort of Masters in Science Journalism that City University in London took up in 2009. And I then spent the summer working at ICTP in Italy. That, you know, there's a strong link there because it was a center set up by Abdus Salam. And so it was really nice to meet people from all over the world. And it was lovely to spend a summer working in Italy. I would highly recommend it if any of you can ever go there. And then after that, I spent a little bit of time looking for a job, and I was really lucky that a position of a reporter came up at Physics World in 2011, and I was lucky enough to get that job. And so I've been with Physics World for pretty much the entirety now of my working career. I started out, as I said, a reporter that I covered mostly science news, research updates, and I did that for almost 5 years, and then I swapped over. I moved into the careers editor in 2016, And since then, we sort of widened our careers to include long form. And so for the last 7 or 8 years, I've also been the features editor. So I cover all of the long form content on our magazine and website. So that includes writing, commissioning, and editing, features, careers, news pieces, all of that. So yes, Physics World, hopefully you're all somewhat aware of the publication, but it is the flagship magazine of the Institute of Physics. And we have a huge global readership. We have about 40,000 physicists in the UK who get print magazine, but we have 100,000 readers online every month. And we like to cover all areas of physics, though some get precedence. Quantum mostly, our readers love a bit of quantum. And so yes, we cover all areas of physics, and our aim is usually, we're a bit technical, bit more technical than say, New Scientist, but definitely still not too technical. We are a magazine, not a journal. And so we aim our content at someone doing an undergraduate in physics and above. We have our monthly magazine, we have our website, and we also have some special briefings that we do in certain areas, such as quantum science and technologies. Since 2017, I've been putting together an annual careers guide. This guide is available freely online for everyone to access. It pulls together all of our careers content of any given year, so that if anyone is looking, whether you're an undergraduate just starting out early career, or just looking for a change in your career, or you want to know what other physicists are doing across the world, this guide contains all of our careers pieces. So you get a much more complete idea of what physicists are doing. It also includes for undergraduates and graduates looking for jobs. This is a bit more focused on the UK, but it includes employer profiles, and this can be from companies, academic institutions all over. So it's quite a complete guide if you're a physicist in the UK, but I still think we do cover a rather international reach of topics. And so it's just interesting to see what physicists are doing across the world. And something that we've launched just this year is Physics World Live. This is our sort of live recordings of panel discussions on certain topics. One of the ones that we just did this year, as you can see earlier this month, was on quantum sensors. So I thought all of you might find that interesting as a topic. You can still view this on demand. And we have 2 others that we're doing this year that include particle physics with the CERN anniversary and battery technologies. And we hope to have quite a few more next year to celebrate the International Year of Quantum. So that's a little bit about Physics World and what we do. What I'd now like to talk to you guys about these 5 women that you see on the screen. So I've been doing careers content for Physics World now for the last 8 years, and I get to talk to a lot of amazing people doing some amazing research across the board. And all 5 of these women, I think, have quite interesting stories and are doing some really interesting things in quantum physics in different areas of quantum, actually. And so I'm going to tell you a little bit about them. So first of all, we have Ilana Wisby. If I'd been doing this talk about a month ago, I would have said that she was the CEO of Oxford Quantum Circuits. I found out 2 weeks ago that she has actually just left them because she feels that she has set the company up so well that she now wants a new challenge. So for the last 7 years, she's been working on setting up what is probably one of the most popular quantum companies in the UK today. She set up the company from basically, it was, as she described it, on day 1 of the company, it was her and a laptop. And it was a bit of a passion project for her. So Ilana, quite interestingly, she did her undergraduate in physics and in music because she, as growing up, she wanted to be a musician. And so she wasn't quite ready to give up the music aspect. So she did her undergraduate and she found somewhere where they let her minor in music and major in physics. So if you read the article with her, she has this great quote where she says that she would work in the lab and then she would be in the clock tower playing gongs for her other class. But so she had this rather rare combination for her undergraduate degree. And then the minute she finished, she moved on. She went on to a quantum detection group at the National Physical Laboratory and worked there for a while. She did her PhD based out of the research that she did there. But the minute she finished her PhD, she actually left academia for a while and sort of went into the city of London. She was working in finance, and so she wanted to learn how to become a bit more of an entrepreneur. And then a little while after that, she was product director of this company called SnapOut, which was the first sort of spin-out company that she worked for. Interestingly enough, SnapOut worked to deliver the diagnosis of early onset diabetes in India using diabetic retinopathy. So she'd already sort of seen what it was like to build a company from scratch without having the pressure of it initially. But when she was ready, she realized that she had all the skills. And so herself and Peter Leake from the University of Bristol, they set up, they decided to, take the gamble and set up Oxford Quantum Circuits. And today it is a huge company. They've, raised, as it says, over 100 million in funds. It's a very settled company, and they offer quite a few services. When they just started, it was, I think Ilana's idea was just to offer hardware, but they now offer everything from their cloud services to, they work with financial companies, automotive, energy, health, national security. And so I think Elena's story is really quite interesting for someone who had quite an interesting entry into physics. And I think she's someone to look out for to see what she does next now that she is no longer at OQC. So that's Ilana. The next person I thought I'd really like to highlight is Prineha Narang. So she is a professor at UCLA, where she runs her own lab, the Narang Lab, and they do some really interesting work. She's sort of has this background in material science, but what her lab does now is really interdisciplinary. It's computational science, condensed matter, quantum photonics, information science, and all of that sort of linked through quantum materials. She's won numerous awards. She's been recently appointed as a US State Science Envoy because she really enjoys communications, and she really enjoys, talking about her science. She was on the Forbes 30 under 30 list in 2017. What was really interesting about Prineha is that, when she was in school, sort of between 11 and 14, she didn't plan on becoming a physicist or a scientist at all. Her interest was in sports. She was a track runner, and so she thought she was gonna, have a career in sports. And funnily enough, it was her actual athletics coach who said, actually, I think you're quite good at STEM subjects too. Maybe you should look into a career in that. And so it was her athletics coach who encouraged her to, pursue science, and clearly that was the right decision for Prineha. She did a PhD at Caltech. She spent some time at MIT after that. And one of the things that Prineha really talks about in her conversation with us at Physics World was that she did feel that it was really hard for her to find a mentor because she didn't have anyone who looked like her, and that there were no women working at that point at all. All of her professors were male, etc. So she said that, there just wasn't any female faculty members to assure her that she sort of belonged in this space. So that was something that, she really wanted to make sure that her lab could be a place where other women and other minorities could make sure that they felt welcome there, and that she could serve as a mentor to them. So that's quite a bit of what they do now. And what she says that what she really likes focusing on today is that, her group does excellent science, as she puts it, but very importantly, while having fun. She likes to emphasize that, a lot of it comes from her own experience, that she wants people to feel that excitement when working on a new topic, especially when they have a result. So she encourages her group to have a lot of fun. And so she's you know, from deciding to be a sportswoman, she's now running her own lab at UCLA. So that's Prineha. The next person I thought we could talk about is Masako Yamada. So Masako is the director of applications at IonQ. IonQ is probably quite a famous, I would say, quantum company today. They're on the New York Stock Exchange. And if anyone talks about ion-based quantum computing, I think IonQ's name pops up. So she has, again, quite an interesting background. She spent 20 years working as in a very high role at GE Research. And then she took quite a gamble to move into quantum computing. That wasn't necessarily exactly what her research at GE had been in. And so she had to sort of reinvent herself a bit late in life, as she puts it. But she now is the director of applications at IonQ. And so that means she runs a team that works with the clients. So her team is the one that goes to clients and says, right, what is the problem? What is the problem that you need solving? And how can quantum technologies at IonQ help them solve this problem? So she works across the board. She works with scientists and engineers at IonQ, but she also works with, you know, product managers, sales engineers, marketing people, operationals, and as she puts it, even legal and finance. And what was interesting in her chat with us was that she said that, you know, working in the quantum sphere right now at IonQ, she said, I'll quote her directly. She said that IonQ is a growing company in an exploding field, and rubbing shoulders with some of the pioneers in this space probably feels a bit like working with Thomas Edison when he was founding GE. So you can really feel her excitement for what she's doing. And she also points out in her interview with us that, you know, there's this misconception that once you get a PhD in one area of physics that you can't, you know, you'll be defined by that topic. And she would like to point to her own career to show that it is absolutely possible to learn on the job, to use the skills that you have and transfer them to different areas. And she feels that the current quantum sphere is a really positive one to do that if you're a young student. So that's Masako. The next person we'd like to talk about is Leah Lee. I really wanted to include this particular picture because she took that picture of when she set up her new company in the middle of COVID with her new puppy. So she said that was her new company and her new puppy, and that was how she got through COVID. So Leah is a physicist, and she is the CEO and founder of 0 Point Motion. Basically, they build optomechanical sensors, optomechanical cavity sensors. And the idea here is to come up with sensors that, you know, can help you navigate and help you figure out where you are without the need of constantly, you know, being in touch with global positioning satellites. Her technology is based, you know, she likes to describe it as a miniature version of LIGO because it's quite similar, the cavity-based interferometry that they do. Leah's company has been quite successful already. She's raised over £3.4 million of funding now from different grants and councils in the UK. Leah's story is also an interesting one. Both of her parents are physicists, and so she grew up in the labs and in the dorms. She remembers when she was little, she actually lived on your university campus with her parents. So she, and that was in Bristol. So she grew up around a very sort of academic environment, and that clearly resonated with her. So she knew that she was going to, you know, be a scientist too from quite a young age. And so, yeah, she studied physics at Imperial College, and then it was her final year project where she really developed her love of photonics. And so she worked at BAE Systems after that, but decided she wanted to come back and get a PhD in quantum physics from UCL. And so her first steps into entrepreneurship came in 2016 when she participated in an Entrepreneur First Innovation Forum that was hosted by Nature. And this was a little bit like Dragon's Den, where you come and sort of pitch your idea. And, you know, she decided that she really wanted to be an entrepreneur too. She really wanted to run her own company. And she also felt that if she could do this, then it would mean that for a lot of other, young women who come from a POC background, that she could be a good positive influence for them. She could, she wanted to be a mentor for other future women like her. And so yeah, that's Leah's story. And currently her company is they're in the process of coming up with their very early testing systems. So they're doing really well, and I think it'll be a company to look out for if you're looking for any jobs in this field in the UK. And the last person I'll talk about is Merit Moore. Now she's an ex-quantum scientist at this point, but she just has a very interesting story and background, which is why I like talking about Merit. So she is someone who, from a very young age, she had a great passion for science and for physics, but she also really loved ballet, and she found it really hard to pick between the two. There were various times in her life, for example, when she first started doing her physics degree at Harvard in 2006, she felt that there's no way she could do that and be a ballerina at the same time and sort of do dance at a professional level. So she sort of quit, but she kept it up as an extracurricular. But then came an opportunity to dance for the Zurich Ballet Company, and so she put a pause on the physics. So she kept bouncing between the two and decided in the end that she was not going to give up on either one of these aspects, that she was going to be a professional ballerina while also being a physicist. So she did her PhD in quantum optics at Oxford, where she was working on building basically quantum metrology. She was looking at single photon sources for experiments. And at the same time, she would take breaks, sometimes for a couple of weeks, sometimes for months, and go and perform with different ballet companies from all over the world. And so she decided, once she finished her PhD, that she was going to keep both of these aspects of her life. She danced with the English National Ballet once she finished her PhD, and she was also on a TV show aired here in the UK on the BBC, where it was called Astronauts, Do You Have What It Takes, in 2017, and it was an actual selection process to see who might go into space. And so she was one of the candidates on that. So Merit's entire philosophy is that you should be able to do all of the things that you love, and there should be, she encourages a lot of ways to allow for this sort of life of being able to do all the things that you enjoy without giving up on one or the other. She now works at a robotics lab in Abu Dhabi, and that came out of a project that she was doing in 2020 during the pandemic, where she met a design officer for a company that was building social skills for robots, and she realized that she enjoyed robotics too, and she had the skills to do robotics, but she could also, as she puts it, dance with robots, because robots don't get COVID. So it was a way for her to still be involved in the science and involved in the dance, even during a global pandemic. So that's Merit's story. And yeah, so those are the 5 women that I wanted to highlight. And I feel like there are so many other women across the world that we at Physics World would love to cover, including all of yourselves, because there's so much interesting research being done everywhere, and we're always willing to hear from everyone. And I thought I'd end the last slide sort of looking at the fact that, with the International Year of Quantum next year, and the fact that so many governments across the world, including the government in India, have large national strategies with lots of funding across the board in quantum. And so I hope to see more and more amazing women in quantum science that I can have the pleasure to talk to. Thank you.
Thank you very much, Tushna, for a very, very interesting presentation.
Oh, my pleasure.
Questions from the audience? Yes, you're currently in UK, right?
Yes. I'm in Bristol.
Bristol.
Yes.
So any questions? So I have one comment. So out of the, what I noticed is that out of the 5 women you covered, almost 4 of them, if I recall correctly, have opened their own companies. So
Yes.
their academic career and scientific bent of mind, all of them have an entrepreneurial bent of mind.
Absolutely, absolutely. And, I personally found their stories really interesting precisely because of that reason, because so many times we cover so many spin-off companies and companies like that, and usually it's sort of always men leading the charge and sort of all male panels, and it was so refreshing for me to see these young women who took these big risks and went and found their own funding, set up the companies, got the background, and they all seem to be extremely successful and having they haven't sort of disappeared into the night as quickly as some startups do. So that it's clearly something that I think, more female scientists could think about if you are maybe transitioning out of a career in academia and you're thinking about industry, think about setting up your own company.
Thank you. Another question here, the picture which you showed about the ballet pose, is that a robot next who is dancing?
Yes, that's right. That's
The
literally
robot has been programmed to follow.
Yes, that's
okay,
what she.
that's
I would
very-
say, yeah, definitely look up. She has a great website with lots of videos on it,
Okay.
and so that's kind of a little bit what she's doing now. Is, social skills for robots is how she describes it.
That's very interesting. I should definitely look up. Thanks a lot, Tushna, once again for an interesting.
Thank you very much. Thank you.
Thank you for everyone. So if you were here in person, we would have presented a memento to you.
Oh,
Hopefully,
thank
if you
you.
visit us, we'll
Oh,
keep
that would
telling
be
a
lovely.
story.
That would be lovely. I was actually in Bombay last week and the week before, but I
just
did have to. I know. Yes, unfortunately, I had to be back here for other work commitments. Otherwise, it would have been a great pleasure for me to attend. And I think some of my colleagues are attending one of the other conferences you have later on in the year, including Antigone, who works on our journals.
Okay.
So,
Okay.
yes.
Thanks a lot.
Yes, and feel free to reach out to me if you're doing any interesting science and would like to talk to us about it or talk to us about your careers. Just drop me an email.
Absolutely. Thank you once again.
Thank you.
Okay, so this brings us to the end of this. Okay, Pranita wants to say something.
So now I would like to request our Dean Academic Program, Professor Amita Pulaveri, to please hand over the memento to the session chair.
Thank you very much. Thank you very much. So now I would like to request our director, Professor Tanushree Shahadas Gupta, to say a few concluding remarks about the conference.
So I think it has been a very long day for all of us, and I think all of us are eager to go back home. But I think all of you who attended for all 3 days, you will admit that it has been a very, very exciting time. And few of us have left, but before they have left, they all have said that this is probably one of the most wonderful conference they have attended. In fact, when they came here to attend the conference, they didn't had clear idea what to expect out of it. But it was a very good blend of science as well as the personal struggle of the women. And that blend, they all appreciated a lot. They appreciate it so much, they want to have it as an yearly event. So we have to see how to make it. And in this context, in fact, in my opening remark, I also made that in Europe now, they have made a network which is called Quantum Women. We can actually think of even such a thing in India if we want to make this a yearly event. And DST secretary also mentioned that whatever recommendation that comes out of this conference, he actually kind of urged us to send it to DST. and very few people are left here. I can see from the first 2 days, but we have made a WhatsApp group, and please complete that WhatsApp group, and we will make some kind of initial draft, but feel free to add to it in whatever way we can strengthen this activity. And as Tushna also presented, worldwide, there is a very significant strength that is there. I mean, of course, it is irrespective of man or woman, but it seems to be women are really coming forward. It has been mentioned many times, especially in this kind of quantum revolution. They're taking part in a big way. So that's a very, very good sign, and we want to keep it alive. So with that, I will end my concluding remarks, but these concluding remarks will remain incomplete if I don't thank two of the main person who really worked seamlessly. One is Dr. Saqib Samim. Please come here. And he really, really worked very hard, but he also needed a stable partner at the other side of the crease, and that was Parijat. So thank you. Thanks to both of you, for making it. So Parijat, please come here. So for making it, so wonderful, so smooth. And I can tell you, each and everyone attended personally has told me that they really, really have liked all the arrangement, the scientific program, everything. So both of them, they deserve a big round of applause.
Thank you very much.
Thank you.
But actually, majority of the work was done by other people. We were there. So,
Because that was behind the screen.
so for that, the co-convener, Dr. Parijat, they will present the vote of thanks.
Okay, so as we draw to the close of this engaging scientific conference, it is my privilege to deliver the vote of thanks on behalf of the organizers. So firstly, I extend our heartfelt gratitude to all our distinguished guests, speakers, session chairs, panelists, and our valued participants. So your insights and knowledge have been both inspiring and thought-provoking, setting a high standard of discussions that followed. A special thanks goes to our director, without whom this event would not have been possible. So your support has been invaluable, and we deeply appreciate your contribution to the success of this conference. So, thanks to our national and international advisory committee members, local scientific committee members, organizing committee members. Your tireless efforts behind the scenes have ensured the smooth running of this event, and your commitment and hard work are truly commendable. I must also acknowledge the support staff and the volunteers. So your efficiency and willingness to assist at every turn have been very crucial in making this conference run successfully. So this year-long program, BOSEStat at 100, is a collective effort by all the members of the SN-BOS family. And finally, to all the participants, your enthusiasm and active engagement have made this conference a memorable and fruitful experience. So your contributions during the discussions have been invaluable, and we look forward to seeing the collaborations and innovations that arise from this event. So thank you all for your presence and participation. And we hope to see you again at our next conference. Thank you.